Hi everyone, we're going to start with the second speaker in around 4 minutes. Is the second speaker ready?
Yes.
All right, so let me introduce you. We're going to start with the second speaker, Martin Dominguez, Pablo Celayes, Damian Barsotti, who are going to present user agnostic models for retweets prediction based on graph embedded representation of social neighborhood information. Uh, uh, Pablo, are you going to present?
Yes, I'm sharing my screen already. I don't know if you can
Yeah,
see.
yeah.
Great.
I can
Okay.
see perfectly.
Great.
Yeah,
Okay.
you have 15 minutes, around 15 minutes, 5 minutes for questions. Thank you.
Perfect. Okay. Thanks a lot for the introduction. And yeah, let's start with the presentation of the paper results. And before we start, we wanted to give a bit of context of our previous works and how we arrived to the current state of our work on the problem of um, prediction of social activity in social networks, in particular on X, formerly Twitter, where we have been working for some years now. Basically, we started on 2017 with a paper where we worked on the problem of predicting preferences, retweet preferences of particular users given the activity in their neighborhood, only based on on Boolean features of which neighbors have preferred or retweeted some content or not. We were very happy with the results of that work because we realized that even without using content features, just with features about the activity in the social neighborhood, we were able to achieve very good prediction performance, like of around 87% F1 score. Later on, we took a different direction and we did another work where instead of having like individual models per user, we had one general model, but this general model was also predicting like also a general target. So we were not working on predicting individual preferences anymore, but more trending or popular tweets. Later on, we continued with another work where we explored the importance of the time after the generation of a piece of content for the quality of the predictions. And finally, last year, which is the work that this work from now mostly builds upon, we started working on an idea of improving our original framework for modeling the problem, where instead of having just one model per user, we wanted to have a model that is able to predict individual preferences, but using some sort of more general representation that allows us, among other things, to train more efficiently and also to better generalize. And what we're going to present now is an improvement on that model, which is also like a general model, but with less feature engineering effort involved by leveraging some state-of-the-art graph embedding techniques. So before we start, we can mention a bit about the main data set that we built some years ago and that we have been using for these models and these experiments that we've been doing. We have a social graph of Twitter users with the relation of who follows who. We built this basically following 3 steps from a seed user. And then since we wanted to have like homogeneous enough representation of neighbors for each member of the graph, we work mostly on a subgraph where we ensure that each user has at least 50 other users in their neighborhood in this filter graph that we use. The graph built this way has around like 5,000 users, 230K edges. And then the content that we are using for the predictions is 1 month of tweets in Spanish language from all the timelines of all these users in this graph, which amounts to over 1.5 million tweets. So as I said before, the universe graph where we're going to be working is this graph of around 5,000 users. But also in terms of like being able to successfully train a model that can predict retweets, we need to focus on users that are at least somewhat active. So basically, users that don't have at least 10 retweets in this 1 month period are omitted from the predictions, but not from the modeling. So their information will still be used as input for the predictions, but they won't be used as a target for predictions. At the same time, to reduce noise, any tweet that has only been shared by this kind of like passive users is removed. So as a result, we end up with this subset of the users in the graph G, which is a bit over like 3,000 users. And on the first work that we did, where we basically were training just one model per user, that was like very computationally expensive. So we had to restrict our modeling to a selected subset of these users. So in the original work, we were providing predictions for only around 200 users. In this work and the previous one, we are basically predicting for the whole subset A of active users. But we mentioned this for historic reasons because basically you're going to see many comparisons that are against the first individual models that we developed. So having said that, we also have to be a bit careful about how to split our data set for evaluation. And because, as I said before, on one hand, for historic reasons, we have this selected set of central and active users, and we have the remaining users. And on the other hand, we also, I mean, there are many different ways in which we want to test the generalization capabilities of these models. So on one hand, we want to be able to verify if the model is capable of predicting future retweets of users that were seen during training. That's why there is a split 70%, 30% at the tweet level. But also, on the other hand, we also want to be able to see if the model can even generalize to unknown users. And that's how also there is a split at the user level. So it's a 70-30% split in the case of the general set of active users, and it's a 50-50 for this historical set of active and central that were used for the individual models. So all the results that you will see, basically, we are using a training set, the highlighted in green sections. So the training tweets by training users, okay? And then depending on the kind of evaluation we want to do, we might choose, like, for instance, the set of tweets in the future by these users, or the set of all tweets if we want to also evaluate the generalization to unknown users. And so, yeah, having said that, let's go straight to the modeling part. And again, we're going to show quickly a bit of history. The first models that we worked in some years ago, the ones that, as I mentioned before, were one model per user, were actually very simple models. Were basically for each tweet in our data set, we build binary features based on which of the neighbors to the user we're trying to predict for retweeted this or not. I didn't mention, but the process we use to build up the neighborhood is basically just this second degree over the followed relationship. And the target is basically if the central user, the user we're trying to predict for, is going to retweet this tweet or not. As you can see, this is heavily dependent on the user we're predicting for, because basically the cardinality of the feature vectors is basically the amount of neighbors in the neighborhood of this user. So it's not very convenient to generalize. That's why in our previous work, what we did is coming up with a heuristic where basically we're trying to transform all these like Boolean feature vectors into a more general representation of fixed length. What we were doing in that work is basically ranking the neighbors by an importance score, which is a weighted sum between centrality graph, network centrality measures, and activity measures, basically historic number of tweets and and retweets. And based on this, we were like ranking the users. And basically, there were two hyperparameters here. The top K of them were kept with their Boolean features as in the individual work. And the rest of them were grouped in buckets, where each bucket would have as a feature the number of retweets within the bucket. So with this, basically, we got a representation that is of fixed length, basically the sum of these two parameters, the selected users and the number of buckets. And we were getting like very, very good results in the sense that being just a general model, it was achieving similar performance to the individual models. The thing here is that this model still has a feature extraction process that depends on the selected user because it depends on this activity and centrality ranking of their neighbors. And this is what can be improved and what we seek to improve in this current work. So what we did now is basically trying to leverage graph embeddings. There is this complex algorithm. There are many, but we chose this one because it's quite efficient and it's good at capturing relations that are not symmetric, like the follow relation in a social network like Twitter. And basically, with this, we can build a vector representation for each node in our social graph. And then we wanted to use these representations to come up with a good representation of the activity about the tweet, again, on the neighborhood of a given user. And basically, we now need also like a representation of the user we're trying to predict for also because we're developing a general model. So we came up with this very simple scheme where basically, once we have trained these embeddings, we take as features for a tweet relative to a user the concatenation of the embedding of the user, the average of the embeddings of all the neighbors, and the average of the embeddings of all the retweeting neighbors. So this would be the ones that would be flagged as 1 or 0 in the previous schemes. So same as before, the dimensionality is not dependent on the user. It's simply 3 times the dimension of the embeddings. But the added benefit is that there are no additional feature engineering work depending on the user. It's basically we just generate these embeddings once, and then the only thing we have to do per user is pick the neighbors, pick the retweeted neighbors, and take the averages. So with the little time we have left, we're going to jump to the results. We can skip this one. Basically, we just did, same as in previous work, a round of hyperparameter tuning where we were tuning an XGBoost classifier hyperparameters, but on top of it, adding the dimensions of the embeddings as an extra hyperparameter. And armed with this model, we proceed to first compare like the general performance. So basically the F1 score on the combined test set is 83.8%, which is very similar to the previous general model, the one built on the heuristic that I showed before. Also, when we go to compare actually with the individual models, we still see, same as in the previous work, like on average, there is a slightly lower performance than the individual models, but it's already better than the one with the heuristic. As you can see, it's like 0.7% on top of the heuristic. And if we take like some quartiles and medians here, we can see that actually the quality for median and third quartile is very similar. So basically the advantage of the individual models is mostly on more like difficult to learn users where the performance is low. Then we also did an analysis of like known versus unknown users, and same as in previous work, we don't see like big differences between train and test users, so the model is generalizing well. But there are differences between like these very central users that we have for historic reasons and the more general ones. Okay, we're almost on time. So our obvious conclusion here is that graph node embeddings can be a good representation for this kind of problems. And yeah, as we said before, they can like give similar results with much less feature engineering work. And here we have some possible directions for next steps, but we can save those for the questions if we are on time.
Thank you, Pablo. Is there any question for the public? You can raise your hand or you can write your question if you like. Uh, well, I do have a question, Pablo. You previously say that you are doing more research in this direction, and you already did research in the same topic. Can you explain more about other techniques that you are or your college have used to address this issue?
You mean like in previous works or?
Yeah, or yeah, maybe.
Yeah, so well, basically one of the things that we also changed over the years is that our first models were support vector machines, and in our last works we switched to XGBoost, which is like an implementation of gradient boosted trees. And we've also been experimenting a bit with using graph neural networks. Actually, this work is a first step in that direction. But yeah, we're still working on that. So basically, in terms of classification, we have mainly been using support vector machines and XGBoost. And then there's also like a bunch of other work where we have also been using features about the content, where we were like using, yeah, back in the day, text embeddings, basically fast text, but probably that would need an update by now.
Thank you, Pablo. It was very interesting
Thank
your
you for your
talk.
question.
Uh, I think there are no more questions about it. Martin Dominguez is asking about if we are transmitting presentially. We are not. We are only transmitting on YouTube. So
The conference was not presential in this
uh,
year.
yeah, yesterday the conference was presential, but the thing is that we don't have a space. So most of the members of the laboratory are in
Good.
seminars. So that was the problem. But we
The
are
next year
transmitting.
will be again in Mexico, or will be in Peru as the previous one.
Uh,
Do you know that?
I don't know exactly if that is already decided. So
Okay, good.
maybe it will change the place. So, but I really don't know about it.
Good. Thank you.
Thank you, Pablo. And
Thank you.
So I think I'm the next presenter. Fernando, are you the
yeah,
host?
you're the next speaker. So can you can you share a screen?
Yeah. 1 second.
All right. So the next talk is going to be conducted by Nicolas Roque dos Santos, who is going to present his research entitled as Item Response Theory in Sample Reweighting to build fairer classifiers. Thank you. Thank you, Nicholas. You can present now.
So, hello everyone. Good morning to you all. I'm sorry in advance if I start coughing during the presentation. I'm a little bit sick. So, as Pablo said, I'm going to present the item response theory in simple reweighting to build fair classifiers paper. I'm a PhD student at University of São Paulo, and this work was developed by Diego Minatel, who's the first author, and he's also a PhD candidate at University of São Paulo. Vinícius Ferreira da Silva, who is also a PhD candidate at University of São Paulo, and also by Professors Mariana Curi, who's Diego's co-advisor, and Professor Alneu Lopes, who's my supervisor and Diego's supervisor as well. So can you guys see my mouse on the screen?
Can you? Yeah, we can see your mouse.
Okay. So here's what I'm going to talk about today. So first, I'm gonna present the context where our paper lies. Then I'll present our proposal, the experimental settings. Finally, I'm gonna present the results and conclude my presentation. So as I think everyone here knows, in some circumstances, machine learning can perpetuate societal biases and discrimination that exist within our society. And one well-known example is the COMPASS system. COMPASS, for those who don't know, stands for Correctional Offender Management Profiling for Alternative Sanctions. COMPASS is a system that is used to assess a criminal's defendant's likelihood of becoming a recidivist, or in other words, what are the chances of someone becoming a criminal again after being released from prison? And COMPASS is used in the United States, in many United States to support the decision of judges during criminal sentencing. And sadly, this system is biased against Black defendants. So one of the biggest challenge in the field of machine learning is how do we develop fair decision-making models? How do we create such systems where people are not unprivileged people are not there's no bias against them, and especially when these decisions made by such systems involve people's futures. One way to minimize the biases contained in the data is through the preprocessing algorithms. And when these algorithms are developed for this purpose, they can incorporate some fairness notions, and also some of them can eliminate explicit discriminatory biases. And here in this work, we are using a concept called item response theory, or IRT for short. IRT is a collection of mathematical models that is utilized in traditional test evaluation, so SAT, TOEFL, and exams like that. And IRT is primarily used in educational and psychometric applications, and it has a great power of evaluation and is a fair tool, as has been found in the literature, for evaluating tests that are in a way that is better than the classical test theory. And as I said, the IRT has been used before in on the SAT, TOEFL, and NM. NM is SAT in Brazil, basically. And the IRT can be a promising path to develop fair machine learning models, as this reference here said before. So in this paper, our proposal is to create a new sample reweighting method. By this, I mean we learn weights to each instance in a data set. And we named this method name item response theory sample reweighting, or IRT-SR for short. This method is based on concepts from the item response theory, IRT, as I said. And we apply this method on binary classification. In future work, we are going to expand beyond binary classification. But for now, it's just binary classification. The underlying idea of this method is that IRT, as I said before, is a fairer evaluation method. And sample weights learned, defined using this mathematical model can contribute to developing fairer classifiers. Sorry. So how does our method work? How do we use IRT on machine learning? First, we trained a set of K-based classifiers using the training sample. So we performed the holdout, and on the training sample, we trained K-based classifiers. Then we perform predictions on that same sample with the same classifiers, as I said. And this step allows us to model the set of predictions as a dichotomous test problem for IRT. And I'll show in the next slides how we do it. In this work, we used K equals 4, so we had 4 classifiers. The 4 classifiers we used were based on KNN, so we use 1NN, 3NN, 5NN, and 7NN. And a side note here, in future work, we are going to allow the user to define the base classifier as a hyperparameter, not only KNN, but other types of classifiers and algorithms. But for now, it's just 4 types of KNN. Then we create this matrix here. This matrix here is a matrix where on the rows we have the instances, and on the columns we have the classifiers. And each cell in this matrix here, so cell ij, tells me if the classifier on column J got the right prediction for instance I. So for instance, right here, the classifier 1NN got right prediction for instance 1, and the second one, 3NN got it right as well. The 5NN didn't get it right, and the 7NN also got it right. So we create this matrix here in the second step, and this matrix is used in the third step, where we employ the 2-parameter logistic model. This is the IRT that I was talking about. One of the models that is available in IRT is the 2PL, the 2-parameter logistic model. And we apply this model on the previous matrix that I showed you, where the 2PL model is described by this equation right here, which is basically a logistic function, where it gives us the probability of the classifier getting the right prediction for an item based on its ability to predict instances. The ability is given by the theta parameter here. So Uij equals 1 is the chance of the classifier get the item right, and the theta is its ability. And we define this equation as as I said, is a logistic function, and it has the A and the B parameter. So the A and B parameter is what we optimize, and I'm going to tell you soon how we optimize these parameters here. This 2PL model here allows us to estimate the theta values of the instances, and the theta value here is the weights that we use in our method that is applied to each instance when we are performing the sample reweighting, as I said before. And also this model here gives us this figure here, this item characteristic curve, which is associated with the base classifiers, which shows us sorry, give us the probability of a classifier get a correct prediction, which is the y-axis, based on its ability, which is the x-axis here. And the ability, as I said, is given by theta. So the instance 3, the green bar here, the classifier got it right. So the classifier has a higher chance, a 100% chance to get to predict the instance right. And on the opposite side, the classifier has a 0% chance to get instance 1 right, to predict it right. And in order to calibrate these parameters, to calibrate the parameters of the 2PL model, we use the expectation maximization algorithm, which is an algorithm in statistics that is used to optimize such model. And after we optimize, we calibrate these parameters, we perform a rescaling where we translate the theta values to a new scale. This new scale was in this interval right here between 1 and 5. We rescaled to this interval because it gave us a good trade-off between improvement in fairness measures without significant performance loss. And the final weight for each instance in our data set, in the data sets we use, not only one, is given by this equation right here, which is basically 1 over the rescaled value. So this 4 steps that I talked about is how how our method works. And here's an image, a figure that shows how we perform this experiment. So first, given a data set, we performed the holdout where 80% was used for training and 20% was used for test. In the training set, we performed a 5-fold cross-validation. We used 5-fold because not all the data sets were big enough, so 5-fold was better. Then we used 3 methods, our method, which is the first one, IRT-SR, the reweighing method, which is another method in the literature, and also we use the without method here is just, we don't do anything in terms of sample reweighting, just to have a comparison without doing anything to the data set. Then we applied the AdaBoost, CART, Random Forest, SVM, and XGBoost algorithms to perform classification, sorry. And then we evaluate the results. After performing a model selection, which is this box right here, this rectangle, sort of a rectangle, we retrain the algorithms and perform the final evaluation on the test set. So this is the experimental settings we performed in our paper. Now, going to the data sets, we use 12 data sets, which are these ones right here. The hashtag I here means number of instances. Hashtag A means number of attributes. Protected attributes means which attribute has sensitive information. So for the first one is the sex of the individual, the next one is age, and so on. And the privileged group in the data set. So for the first one is the male, are males, the second one, people, individuals that are over 25 years old, and so on. As I said before, here are the algorithms we used, and these are the hyperparameters we varied during the experiments we performed, and this is the variation range we used. And in order to evaluate our work, we calculated the macro F1 score and 3 group fairness metrics, which are demographic parity, which states that every group has an equal chance of receiving a positive label, equal opportunity, which states that each group has an equal true positive rate. And the last one is equalized odds, which states that all groups share the same true and false positive rates. And going to the results, here I'm showing on the second column the results for where we didn't perform any sample reweighting. The third column is our method, and the last one is the method from the literature. And as we can see, for the demographic parity, we got we won 7 in 7 out of 12 data sets, and on average we got 68.97% against 63.5 and 62.9 without doing anything to the data set in terms of sample reweighting. For equal opportunity, we lost a little bit more here. Reweighing actually won if we check for each data set, but on average, our method got a better score of 78.5% against 75.8%. And for the last fairness metric, our method also won in 7 out of 12 data sets. And on average, we got 70.72 against 68.30 on the reweighing data set. Reweighting method. So not only checking the fairness metrics, we also conducted the Nemini post hoc test, and as we can see, so the x-axis here means the rank in which each method won. So our method, as we can see, is won in every situation, but this bar right here where I'm passing my mouse under means that there's no critical difference between our method and the reweighing method. The first one is for demographic parity. For the second one, which is weak opportunity, there's no critical difference between the 3 methods we compared. And on the last one, it goes back to the first situation where our method and the reweighing method, there's no critical difference between them. And in terms of macro F1 score, the averages are right here, and without doing anything to the data sets, without performing sample reweighting, we got the highest results. This is expected because we are changing the data set a little bit, so we were expecting to lose in this scenario, but we didn't lose as much as we expected. As you can see, there's like so for the first one here, 69.53 against 68.09. So it is not a big difference if we take into account the fairness metrics that the fairness evaluation that we performed, the sample reweighting and all. So it gives us a good score, given that we are being a little more fair than not doing anything to the data set. So in conclusion, this paper introduced a novel, novel sample reweighting method named IRTSR, Ithon response theory sample reweighting, that uses concepts from the Ithon response theory, as I talked about before. The experimental results indicate that our method is more effective in maximizing the key group fairness, which I showed you. They're not using sample weighting, and also the reweighing method, which is the method from the literature. And lastly, the findings of this study, this work, highlights that IRTSR guides the classification algorithm to fit fairer classifiers. And before I finish here, future work, we intend to optimize the hyperparameters of the base classifier set, which we did not do. We also want to allow the user to choose the K-based classifiers, as I said before, instead of being the fixed for KNN classifiers. And lastly, we also want to test on other classification algorithms on the base set to allow merging classifiers from different paradigms, not only the paradigm we used. And also we want to expand beyond binary classification, which is ideally what we can achieve in next year. Here are the references, and thank you very much.
Thank you, Dr. Nicolas. Is there any question for the public? Well, I will ask some question. Can this theory apply to other classifiers such as deep learning classifiers?
That is a good question, and that's what we are gonna test next year. Diego, who's the main creator of this method, he's using MLP at the moment, not CNN or GNN. But for now, what I know is that it works on MLP, but I'm not sure how is the situation on deeper methods. This is what we're gonna do next year, hopefully.
All right. Thank you so much for your presentation. It was very interesting. We're going to continue with the next speaker, who I think they are already here. The next speaker, I think, is Jianji Li, or Yifu Chen, Niara. Sorry. Is anybody here?
Yeah, we're here.
Yeah. Hi.
Thank you, Jianji Li and Yifu Chen. Who is going to present?
Yeah, Yifu Chen will be the first one.
All right.
Yeah, you will share the.
Okay, let me share the screen.
All right, can you share your screen?
Yeah.
All right. Thank
Okay.
you, Jianji Li. The next speaker is going to talk about analyzing sentiments and topics on Twitter towards rising cost of living. Thank you. You can present.
Yeah, thank you. Hello, everyone. It is our honor and pleasure to be here to present our project, analyzing sentiments and topics on Twitter towards rising cost of living. I am Yifu Chen, and this is Yanyi Li, Nianran, and our mentor, Rizan. So let us begin this presentation. In September 2022, the United Kingdom experienced an unprecedented 40-year high in its inflation rate, resulting in a cost of living crisis that has significantly impacted British citizens. To assess public opinion on this issue, we developed a social media analytics pipeline to collect and analyze microblogs posted on Twitter. Our primary objective was to conduct sentiment analysis on the collected tweets to determine the dominant sentiment towards the topic of the cost of living. Additionally, we performed named entity recognition to identify the entities most frequently mentioned and used topic modeling to uncover the most discussed topics. Next slide. And our approach employed a hybrid sentiment analysis method that utilized 3 lexicons for preliminary tweet labeling and fine-tuned a Roberta model. Our results demonstrate that the superior effectiveness of our methods, which provided an in-depth analysis of the cost of living situation in the UK. And here is the pipeline of our analytic model of the sentiment analysis and named entity recognition and topic modeling on the tweets. Next slide. So for the data collection and pre-process, we used Twitter API for academic research, which enables us to search tweets posted in past few years. To acquire the tweets we specified some configurations to search tweets by dates, geological coordinates, keywords, and hashtags such as food prices, energy bills, cost of living, etc. The raw data contains wealthy information such as replies, retweets, like counts. They are all useful to our research since they contain important expressions of sentiment and perceptions. As mentioned before, there are 3 main tasks in our research. Each of them has different requirements for data pre-processing. For example, emojis and emoticons are important features for sentiment analysis, but they are irrelevant to the topic modeling and named entity recognition tasks. And topic modeling is a case-sensitive task, whereas sentiment analysis is not. So we conducted different process of pre-processing for each task. Yanyi will introduce the framework of our sentiment analysis model and the corresponding results in the next section.
Okay, let's move to the part of sentiment analysis. Basically, there are 3 predominant sentiment analysis methods, which are lexeme-based method, graph-based method, and machine learning-based method. Each of them has their own advantages and disadvantages. For example, when using lexeme-based method, there's no need to use labeling data. Lexeme-based method uses the rules to calculate the sentiment score and use the sentiment score to determine the sentiment of a sentence. But the performance is relatively moderate to some extent. And when using machine learning-based method, there's much better performance gain. But it needs a large amount of data to train a model. In our paper, we assemble the lexeme-based method from weather, Sentinel-net to TextBob, and the machine learning-based model, Robota, to combine the advantages of lexeme-based method and the machine learning-based method. By taking the ensembling method, it gives a relatively faster and efficient solution to unlabeled sentiment analysis problem. In detail, we take the strategy below. To do that, first, we use the lexeme-based method separately to predict the label of each data. Then we start to fill out useful data by taking the majority votes, which means when a piece of data is predicted as the same sentiment by at least 2 lexeme-based methods, we mark these pieces of data as valid. Next, we feed the valid data into the state-of-the-art model, Robota, and fine-tune it to train our classifier. And we use the classifier to predict the disagreed data here. And finally, we concatenate the agreed data with the predict data to form the final result. But before taking the ensembling method, there's a problem need to consider. For example, for tweet, the plot was good, but the characters are uncompelling and the dialogue is not great. We can use weather to calculate the sentiment score. And we use the compound score mainly to determine the sentiment of this tweet. We take the rules below. If the compound score is greater than threshold 1, we can see that the tweet is positive. If the compound score is between threshold 1 and threshold 2, we can confirm that the tweet is in neutral sentiment. Similarly, if the compound score is less than threshold 2, we see that the tweet is negative. But how do we confirm the threshold? In our paper, we use random search as a solution to it. First, we use the 5 pieces of manually labeling data. We have made sure that these 500 pieces of data are ground truth and trustworthy. Next, we set the searching times, for example, 5,000 times. Then we calculate the F1 score for each search. Next, we pick the threshold pairs with highest F1 score. Finally, we apply the threshold gain from the 500 pieces of data to the entire data set. Here we present the performance gained by each Lexing-based method and the majority vote. We find that for weather, when setting threshold 1 and threshold 2 to 0.809 and minus 0.102, it generates the best F1 score, which is 0.588. For text blob, when setting threshold 1 and threshold 2 to 0.262 and minus 0.126, it gives the best F1 score, 0.408. Similarly, for Senti1 net, if the threshold 1 is 0.122 and the threshold 2 is minus 0.121, the best F1 score is 0.338. Besides, we find that after taking majority vote, there are significant performance improvement from 10.544 for weather to 54.762 for text blob and 95.783 for Senti1 net. We find that by taking majority vote, this method significantly improve the F1 score compared to using single Lexing-based method. Here we present the metrics after using the ensembling method. We observe that the overall performance for whatever negative, neutral, or positive is good with F1 score higher than 0.7 for each of them. And we observe that the accuracy score is 0.78. The micro average F1 score for the model is 0.77. And the weighted average F1 score for the model is 0.78. These values, these metrics have demonstrated that our model is capable of solving sentiment analysis. Okay. As a result, our model achieves a macro F1 score of 0.77 in sentiment analysis, and our model significantly improved the F1 score compared to using single lexicon-based method, whether text block and senti1net. And we uncovered significant insight into the sentiment expressed on Twitter. Okay.
And for the topic modeling, we began with a detailed data cleaning, then apply lemmatization and remove stop words. A crucial step as some words can become stop words post lemmatization. For instance, where's changed to where. Our next step involves using bigrams for context-rich topic analysis. The performance of our LDA model was optimized using the Bayesian optimization, focusing on the most informative hyperparameters. This optimization was guided by a coherence score, integrating with both MPMI, which is the normalized pointwise mutual information, and the cosine similarity. Our analysis extra 7 primary topics from Twitter, highlighting the public concerns about the rising cost of living, specifically energy and food prices. These topics underscore the financial struggle faced by many and the expectation from the government and energy companies. For visual representation, we created a word cloud for each topic, which displayed in our figures, showing the public's call for support in this energy crisis. For instance, you can see the most big topic is the crisis, and the second one is the cost and salary, and the third one is affording the monthly bills, and so on. These topics represent the common thought from the public to help the government and energy companies to make better strategies. Thank you.
So there are 3 levels of sentiment analysis: document level, sentence level, and aspect level. In the previous sections, we have performed sentence level sentiment analysis on the tweets we collected. Now we will go further to perform aspect level sentiment analysis. To do that, named entity recognition must be performed to extract entities from sentences, then further combined with our sentiment analyzer model to conduct the aspect level sentiment analysis. In our project, we used Stanford Tagger, a 7-class model that including location, person, organization, etc. And after we extract all entities in all tweets we collected, we select top 20 most frequent entities for further aspect-based sentiment analysis. And this table shows the dominant sentiment towards top 7 mostly mentioned entities. And you can see that people are positive about these entities. Thank you.
Thank you for your presentation, Jifu Chen, Janji Lee, and Nia Rand. Sorry. Is there any question for the public? Sorry for the background noise. Yeah, I do have a question. Did you compare your sentiment analysis proposal with other techniques?
We compared our model with like Yanyi has mentioned before, we compared with the single lexicon-based method, and that is the comparison we made. And we tried to compare the Roberta model we fine-tuned to the raw Roberta find model. That is in our future work. We will try to realize that in the future work.
Thank you for your presentation. It was very interesting. So is the next speaker here?
Hi.
Are you the next speaker? Asif is.
Yeah.
Can you share your screen?
Yes.
So the next presentation is going to be conducted by Asit Suryani, sorry,
Yeah.
a framework to transform metadata and document-level tabular spatial information and measurement to marine geology gauge.
Yeah.
So you can present.
Okay, thanks a lot. And so in this talk we talk about framework that basically use metadata and the document level tabular information to create a marine geology gazetteer. And here I'm Asif Sriani. I'm a PhD student at Christian Albert University Kiel, and I'm being supervised by Klaus Wallmann and Matthias Renz. So yeah. So I have already talked about, because I'm working on a multidisciplinary project from the Helmholtz Marine Data Science. And here we try to aim to find various measurements from the scientific publication. And this is one of the aspects that we explored in the study. So first of all, I want to provide you a bigger picture, like what exactly we plan in that case, because as we all know, scientific publications are basically rich source of information for us, and especially in all disciplines. And recently, this research data management, that is getting very important in every domain, because this highlights like there is whole large amount of data is already there in publication, but that is not being explored well. So we basically try to aim that, and to enhance that case, we are basically targeting the publications. And considering the marine science, I just want to provide two different use cases so that you have a very clear picture. Like the first case, and you see like these two examples are basically the crafted one, like just for the simplicity. And here in the case one, you can see like there is a mass accumulation rate noted as MAR. It has some value, it has some unit, and it also measured at some geographic location by using some method, and it also have a timeline. And this is the straightforward case where we can apply this NLP approach in order to extract these entities. And in the case two, you can see there is SR, stand for the sedimentation rate, that is also a measure at some place, it has some value. And here now you can see like it corresponds to another component in the publication, like for the longitude and latitude values, for the spatial coordinates, you can jump to the table one. So it's mean like going for the text is good, but if you want to have a clear picture, you need to also go for the other components. So so this is as we know, like all the output would be in the PDF. So the focus of all the extraction is basically the PDF files. And how it will work, like we got a PDF file, we try to extract the data that we are interested in, and then we extract the quantities out of it. Then we extract the relevant spatial information, which is also called the contextual information. And then we just try to link them. And finally, it would be look like a kind of a map view, and we can also model into a kind of information network. So regarding the introduction, like scientific publications are basically composed of plain text, figure, tables, captions, metadata. So in this study, we aim at the table and the metadata. And usually all these publications are basically the primary source of information dissemination. And they are primarily designed for the reading purpose, not for the extraction purpose. And it also basically depend upon the publisher, which it basically publish the publications. And now we jump into the precise point, because regarding the tables, this is one of the observation, like authors compile essential numerical information in tables, which they want to emphasize. And regarding the table structure is quite diverse, because it depend upon also the author style, also depend upon the publishers. And every table must have its headers, and it is also it carries different observation in column and rows.
And most importantly, every table is associated to a short description that is called caption. So all these basically components are encapsulated so well, like going for one sort of component, we need to explore more all of its contextual information that is attached to it. And considering the metadata, as we know, like metadata is something like authors, DOI, title and abstract information, which is being used for the indexing. And since we are going to go for the table extraction, which is quite challenging because extraction of the table is another part, and then modeling that information into a usable thing, this is something different thing. So how this information is being represented in tables by focusing in the marine geology, because marine geologists go at which various oceanographic locations and they perform some measurements, and usually one of the bigger contributor is the International Ocean Discovery Program. So they conduct expedition to all over the world. And all because why we are after these measurements, because these measurements are very important for the marine environment, because all the residuals that basically go at the bottom of the sea, they are basically going to be important for the mass accumulation rate and sedimentation rate, and that basically helpful in defining the marine environment. And then regarding this MAR and SR values, it's important to mention like every value must have a spatial aspect, because if we just say like temperature is 15, so we need some more information like where this temperature is being measured. And so these are the basically the units that are being organized here. And if you see, perhaps you notice like for the time, this year is basically the unit for that, because these are the phenomena that are not frequent. So because they are the change in these values occur after years, so that is the reason scientists basically measure them in years. And that also create a lot of hurdles for us, because there is no standard SI unit for these measurements, because every one or every author may use different abbreviation for the years. Some of them use single Y, some of them use YR. So we try to collect most of the observations in that case. And how this is basically a sample table that is shown on my right side. And you can see like every location where the scientists perform some experiment, they give them a kind of a unique name. They call it core IDs. And that would be a kind of a string of alphanumeric. It depends totally upon the authors. And then there is the longitude and latitude information, and then probably there would be a timeline, and then the value that is being measured at that point. So it's going to be a whole information that is being encapsulated into a single table. So how what exactly is done previously? So there are different approaches, standalone approaches that try to do something in that case. So there are one toolbox in the chemical domain that tries to extract the information extraction from text from the chemical domain. So we have our own module geoquantities that basically extract the information from the text. So recently, this is one of the latest one, that is PDF extractor, that basically try to extract most of the information from the PDFs, but other than the tables. And there is a study that is being performed on spreadsheets, and that they just extract this different volumetric data by using a quantum 3 approach. So then we organize like what are exactly the things available that could support us. So for the tables, there are different approaches are available, but two of them that basically works well, that is a Tabula and Camelot. And regarding the metadata, there are a lot of candidates, so that we just use two of them, just Tika and PDF Miner. And how it look like? So this is basically our proposed framework. So we got a PDF, we try to extract the metadata and tables in a CSV format, and then from the metadata, we try to extract the entities that we are looking for. And then from the tables, we have two different approaches. First, we try to extract this longitude latitude information, and then we just try to extract all the information that is available. And then we compile this information. And finally, we have a map view that provide you all the information that is being extracted at a one single place. And for the metadata extraction, we go for the 4 attributes: the DOI, title, abstract, and author's information. And we just talk about all of them very briefly. So for the metadata extraction, so this is one of the observation that we collected. Like all the metadata in publications are basically on the first page of every publication. And for that case, we go for these 4 attributes by using 2 different modules. And the most important, let's say we focus on the title and abstract. And regarding the table extraction, so there are very important things because we every caption in a publication is basically kind of a numeric sequence information, like figure 1, table 1, table 2, and table 3. So for that case, we identify the different focus points, and that focus points are basically passed to a Camelot module, so which basically perform all the extractions. And here we I want to mention, because we for the base we didn't use the base Camelot module. We added the coordinates-based approach, which enhances very well, and I just show you the result later on. And then on my right side on the top, you can see this is basically the raw extracted table from from one of the PDF file that is done by the Camelot and plus our approach. And on the bottom, you can see like this table is being parsed accordingly, so that we have a information that we can use in the next phase. And all the entities that are being extracted by using the Spacey large module, because we are after the oceanographic locational entities such as Black Sea, Kara Sea, or South China Sea. And for that case, we have why we are going for that, because once we extract this longitude latitude, we need to verify like whether this belongs to the region that that people are being talking about in that specific paper, and that title and abstract provide you these boundaries. And on the other hand, we geocoded all these entities to have their latitude and longitude information. And finally, we also introduced a couple of filters so that all the extracted information is basically filtered. And so we remove all the unnecessary entities. And for the information parser, we have a rule-based approach that we form a dictionary of all the headers that we are looking for. And then we parse the information accordingly. And here the most important challenge that we face is about how to handle this latitude and longitude information, because there are 2 different representation of that. First one is it could be in decimal, and it could be in degrees. And one of the observation that we've found is like it's due to the encoding issues, sometimes this degree sign converted into 8 and 0, and sometimes this minute sign goes converted into 1, which basically disturb all the process, and then we can't reproduce this information into the next level. And finally, once we have this thing, this abstract oceanographic location such as Black Sea, this is basically given by our title and abstract, is helpful for us to draw the boundaries for each publications, like where all these measurement has been taken from. And for that case, we created the GeoJSON for various oceans, and that is being used to plot on the map. And once we have this information, we just try to link them and then plot a kind of a huge map for that, and that may carries like a DOI author information of the publication, abstract location, and for each measurement, what is exactly the longitude and latitude information. And one aspect that we could also link is like what is the area is being covered by this this study or this expedition. And very briefly, so we take out 300 documents for the overall this study. And for that, we process all this documents to collect these 4 features. and we achieve better results than this PDF extractor because these results are being compared. And for spacey fine tuning, we annotated like 10,000 chunks. And this annotation is done in the Prodigy tool. And for the table extraction, we we have 72 tables that are relevant to us. And if we don't use our approach, let's say this coordinate-based approach, the Camelot detected like 152 tables. And once we add this coordinate-based approach, so it would be like 82 table that is being detected. And on the other hand, from these 72 tables, we have like 669 overall observations, true observation, I would say. And we are able to extract like 631 location instances. And here, I just mentioned previously about this degrees and this minute issue. So this is basically the issue. We lost this information. And these plots shows like what exactly we extracted from the title and from the abstract. Like this shows like number of entities extracted from the title, the number of entities that are being geocoded. And here, one issue perhaps you notice about these orange lines that are basically because we have some issues with this our spacey model, like East China Sea and China Sea is basically taken as a separate entities, so which basically disturb this thing. And finally, on my right side, you can have a look at all this observation that are being taken, and these basically shows the boundaries, and every marker could backtrack to the paper where this information is being extracted. And you can easily visualize like what are the authors that did experiment at this specific place. And for the conclusions, there are a lot of issues that we incorporate because this is probably the among one module that try to extract this table information, and that extraction of the table information is not straightforward because we have diverse expression of this longitude, latitude information and all the numeric information that we are looking for. And so this initiative will be helpful for the community to gather all the data at one place, because in our case in marine geology, such initiatives are not available before, because there is information available in publication but not compiled at single place. And this could also be taken as a map of measurements, like where all the measurement has been taken, that would be plotted at one single place. And very promising aspect from my thought is this research data management thing, because that approach could easily facilitate this RDM, and that RDM will help a researcher to have the information, I would say, like very quickly, and this will also automate them. And finally, this extraction could also lead to a heterogeneous information network, and that could facilitate like the community detection, like what are the people that are working at the same oceanographic location, so they can collaborate, and it could also result at various recommendation systems. And we just take 30 seconds to see like what it has an impact on RDM. So we take like a few files from publications, just extracted all this information, and there are like around 2,000 information of location instances are there, and we are able to extract this like 1,855 instances. And this is missed due to the encoded issue that is earlier, and which this basically conclude like this information reproducibility will help us in this research data management thing. And so these are the references, and thanks a lot for your time and attention.
Thank you, Asif, for your presentation. It was very interesting. Does anybody in the public have any question? I will ask one question. You mentioned that you collect 300 documents. Is that correct?
Yep.
So did you collect it manually, or you perform some web scraping technique?
Because due to the copyright issue, we cannot do the crawling because since this is something that we are going to public, so for that reason we go for the open source papers that are publicly available, because in that case we will not lie into the legal issues.
Yeah, I know that it might be a problem.
Yeah.
Thank you, Asif. It was very
Yeah.
interesting.
Yeah. Thanks a lot. Thanks.
So the next speaker, I think, is Risa Batista Navarro. Are you here?
Yeah, I'm here. Can you hear me?
Yeah, I can hear you. We can hear you, I think.
Good.
Can you share a screen? Can
Yeah,
you stop sharing the screen, Asif? All right.
yeah, thank you.
Yeah.
Yeah. So just for a bit of context, so actually, Fernando, if you don't mind, I'm going to play a pre-prepared or pre-recorded video from my students because this project was their own work and they decided to pre-record the video, so it will be a shame to not be able to play it. Is that okay?
That's okay. Don't worry. I'm going to
Yeah.
present you.
I'm gonna do that now. Yeah. Just let me know. Can you see the screen?
Yeah, we can see your screen.
Yeah, and you should be able to hear the audio if I play it now. Yeah.
Hello, I'm Lucas.
Yeah.
Jonas and I are going to present a work on the topic Reviewer 2 must be stopped. Transformer-based approaches for predicting paper acceptance. Our supervisor is Risa Batista Navarro.
Peer review is a fundamental process in assessing the quality of papers for publication in academia. However, peer review has few issues we would like to outline. The review process is highly subjective. Study conducted by the NeurIPS conference shows that different review groups have accepted different papers. For the experiment, 2 independent review groups at the NeurIPS conference were given the same papers to assess. The groups agreed on the best papers, but did not come to agreement on which more average papers should be accepted. It is staggering that 50% of the accepted papers differed between the 2 groups. Also, good review scores don't indicate how impactful a paper will be. The same study showed that papers that were scored as good quality did not necessarily perform well in terms of citations. Lastly, reviewers don't get any tangible rewards for putting in an effort in reviews. The review process is anonymous, thus there is no reputation to gain when putting in extra effort in reviews. There is not any monetary reward either. Therefore, it would make more financial sense for the reviewers to utilize their skills towards something that pays. The number of papers being written and requiring reviews has skyrocketed recently. This is evident from the sharp increase in articles submitted to arXiv, a public preprint repository where researchers can share their work before it's published elsewhere. We would like to highlight the fact that the computer science field on arXiv has seen the most dramatic increase in submissions in the last decade. However, just because more papers are being submitted to arXiv does not mean they are all of high scientific value. But when we look at the well-respected journal Nature, known for its strict selection, the growing number of papers they accept suggests that not only are we seeing more research, but that there is a lot more quality work produced each year as well. We are aware of 2 datasets consisting of both accepted and rejected papers by respected conferences. These are Peer-read and ASAP Review. They contain parsed PDF text with a decision of whether a paper was accepted or rejected. Both datasets rely on the Open Review platform, which hosts peer review process publicly. Up to 2020, the most well-known AI conference taking advantage of this platform was iClear. That said, the datasets include papers collected outside of the Open Review platform as well, but either the sample size is too small or they only contain accepted papers, as is for the NeurIPS conference. As for the differences between the 2 datasets, the ASAP Review dataset is effectively a newer iteration of Period. containing unclear submissions with corresponding reviews up to the year 2020, whereas peer-reviewed only included papers from the 2017 ICLR conference. Assuming that a larger number of samples will produce more robust models, we opted to use the ASAP review dataset. We had to do some data preprocessing before training our models. There are about twice as many rejected papers than accepted ones from ICLR. Therefore, to balance the dataset, it was normally subsampled to make the number of labels for each class equal and prevent models from being biased towards rejected papers, resulting in 1,859 samples per class. The dataset was then randomly partitioned into 80-20% stratified splits for training and testing, 20% of the training set being set aside as validation set for the hyperparameter optimization.
In this slide, we present a diagram depicting the whole pipeline of the project. The pipeline begins by taking the data of accepted and rejected papers for training and testing the models. Then we subsample the negative class, as we had twice as many more rejected papers than accepted ones in our dataset. Then this step is followed by two different flows for traditional machine learning models and LLMs. The traditional models require extracting the features by determining them manually. Then they are used as input to various models we chose for the experiment, like SVM. On the other hand, the paper content is required to be tokenized and truncated to be consumed by the LLMs. Afterwards, we use that process dataset of papers for fine-tuning the LLMs. As a result, we obtain binary classifiers for predicting the outcome of the papers for the ICLR conference. Finally, we tested the performance on the test set and interpreted and analyzed the results, which we will share with you shortly.
Before experimenting with transformer-based deep neural networks, we decided to produce baseline results using some old-school machine learning models that have low compute requirements and therefore converge quickly. These include SVMs, KNNs, naive Bayes, random forest, decision trees, and MLPs. Old-school classifiers require samples to be described numerically. Therefore, we had to define a set of features that would vectorize the submission. Our features were handcrafted based on the ones used by peer-reviewed dataset authors for their binary classification model. They include Boolean features indicating whether the abstract contains keywords like deep and multiple integer features representing counts of various metrics, for example, length of the title.
Since transformer models are limited to a fixed number of tokens that can take as input, the original text needed to be shortened, as papers can be thousands or even tens of thousands of tokens. To this end, we experimented with different text splitting configurations for selecting certain sections of the paper only, which would then serve as input text. Also, with respect to the splitting method, the number of tokens stays the same for a certain architecture. The following text splitting methods were tested: introduction with abstract, introduction without abstract, tail, middle, and finally abstract with tail. What is more, we experimented with prepending some metadata about the paper at the beginning of the input text to give models access to more information. The following metadata was added: the title of the paper, whether the paper includes any appendices, and the number of sections and references. The inclusion of this metadata was enabled using a hyperparameter that allowed us to observe whether it improves model performance. 3 pre-trained language models, namely BERT, Roberta, and Longformer, were fine-tuned for predicting paper acceptance. We fine-tuned the base models available from Hugging Face. These models were selected to observe how results differ depending on the architecture. We consider BERT to be the baseline transformer model, whereas Roberta shares the same architecture as BERT, but differs by having an improved pre-training procedure. Both models have a limit of 512 tokens. On the contrary, Longformer can be given longer text of up to 8 times more tokens than the previously mentioned models. This specific architecture allowed us to confirm whether using longer inputs could result in a better performance for a transformer model. We also decided to build a Bayesian ensemble of transformer models to observe if it could outperform any of the single models. You can see how it was constructed and how it works here in the diagram. The rationale for combining multiple models is that errors made by a single model trained on a subset of bootstrap data could be corrected by the other models that were trained on other bootstrap subsets of data within an ensemble. Due to the long training times and the resources required by Longformer, we utilized the parameters of the best performing Roberta model to construct a Bayesian ensemble.
The table depicts the results of traditional machine learning models trained on handcrafted features. The hyperparameter optimization was carried out to identify the best combination of parameter values for each model on the validation dataset. These models were then run on the test set to measure their accuracy. However, SUM, Canon, and Naive Bayes performed poorly, obtaining only around 50% accuracy. Possibly more data samples and features might increase the performance of these models. Nevertheless, decision trees and MLPs obtain significantly higher accuracy than random guessing. Overall, MLP reached the highest accuracy of over 78% on the test set.
The figure shows that more than half of the runs did not learn meaningful patterns in what makes a paper accepted or rejected on the validation set for transformer-based models. Therefore, many trials ended up predicting only one class all the time. This shows that this classification task is difficult even for transformers. Our experimentation revealed that the model often found it challenging to learn from the textual content alone. Satisfactory performance was usually only obtained when metadata was prepended at the beginning of the input. The inclusion of metadata features positively correlated with higher accuracy. As expected, taking only the middle part of the paper did not attain satisfactory results, whereas using the introduction with or without the abstract performed the best out of all truncation methods. The table presents the results of the best performing model for each transformer architecture when evaluated on each of the validation and test sets. The validation accuracy is maximized through hyperparameter search to find the optimal values for parameters which are used to obtain the accuracy on the test sets. The best performing models for each transformer architecture utilize the metadata features, which we expected, as it provides models with more information to help in making a prediction. Roberta outperformed BERT, which is unsurprising, because Roberta's architecture was designed to improve upon BERT. Moreover, as anticipated, Longformer surpassed the performance of other architectures with almost 77% accuracy on the test set. Furthermore, an ensemble of 10 Roberta models attained a test accuracy about 1 percentage point lower than a single Roberta model trained on the entire training data. However, it was found that some models did not manage to learn sufficiently from the data within an ensemble. That is, some of them guessed one class all the time, which decreased the combined performance of the ensemble. Other transformer architectures and different ensemble methodologies might outperform this obtained performance. As depicted in the table, the precision and recall of the best performing transformer model, which is Longformer, are about 83 and 68% respectively, indicating the model tends to reject good papers as reviewer 2 does as well. This finding can be attributed to the model potentially suffering from the reviewer 2 problem that is very likely to be inherent in this dataset. In conclusion, in this work, we trained and fine-tuned various models to predict paper acceptance, spanning traditional machine learning and transformer-based approaches. Longformer achieved nearly 77% accuracy, surpassing BERT, Roberta, and a Bayesian ensemble of Roberta models in differentiating between accepted and rejected papers. Incorporating metadata features, such as appendices presence, significantly enhanced the predictive capability of the models. In addition, handcrafted features served as input for models like SVMs, decision trees, and MLPs. Overall, MLP reached an accuracy of over 78% on the test set, slightly outperforming the performance of transformer models.
We believe there are many ways of constructing a more robust classifier. For instance, better performance could result from utilizing hierarchical transformers and encoding the entire document. The system could employ an instruction-tuned LLM such as GPT-4 to use an even larger context window and to provide rational and arguments for paper acceptance or rejection. Lastly, gathering a more diverse data set of peer review decisions from open review is possible, since now ACL and NeurIPS conferences use the platform to conduct their reviews publicly as well. These are the resources used to present our paper. If you have any questions for us, you can get in touch and we will be happy to answer them.
Thank you. I think that's the end of the presentation. Yeah.
Thank you, Dr. Reza. Is there any question for the public? I don't know. I don't see any question. Doctor, is this the first time? Sorry for the background noise.
That's fine.
Is this the first time this data set is worked with?
Has been used. I think it has been used before, but not with the transformer-based model. So I think the kind of what we wanted to explore in this work is the feasibility of using transformer-based models on this data set and to see how the performance compares with more traditional machine learning-based algorithms. And as you can see, the traditional one, you know, MLP actually outperformed transformer. So that's quite interesting.
Yeah, that's quite interesting, but transformer surpass the accuracy achieved with the
Thank you.
The multi-layer example. Thank you very much. It was very interesting.
Thank you.
So thank you. I think the next speaker is already here. Is Ariel? Are you going to present? Dr. Ariel? You're mute.
Hello?
Yeah.
Can you hear me?
Hear you.
Oh, I'm sorry. How are you,
Can
Fernando?
Hi, Doctor. Can you share screen?
Okay.
So the next presentation is going, it's entitled as Reinforcement Learning and Biological Inspired Artificial Neural Networks. It will be conducted by Dr. Ariel Fury. So please, you can start.
Okay, can you see my screen?
Yeah, we can see your screen.
Okay, thank you very much. Okay, thank you, Fernando, for your presentation. As Fernando said, my name is Ariel Fury. I work at Universidad Nacional de Córdoba, together with Martín Domínguez and Francisco Tamarit. I want to thank all of you for attending this talk. I'm going to share with you some topics we are working on. Our main idea was to attempt to explore the integration of biological inspiration with reinforcement learning. I'm going to start describing key concepts and finish presenting some of our results. This work is based on three pillars. The first is the artificial neural networks we use. We start using a particular network whose architecture comes from the biology. This looks like this. I'm sorry, you are not seeing my pointer here. This looks like this. The architecture has the network has 11 neurons. These two and these two are sensory. You can think about that as input, an input layer, and another two are motor. You can think about that as an output layer, and 5 internal neurons. We also have 3 kind of connections: inhibitory, excitatory, and electrical or gap junction. And this architecture is called tap withdrawal circuit. At some point of our path, we wonder if the architecture must be mandatory tag withdrawal circuit. Trying to answer the question, we start using a network with a shuffle architecture. I mean, we take exactly the same neurons we have in tag withdrawal circuit, but randomly change the connection between them, something like that. Here we have an instance. The neurons are the same, but you can see the connection are really distinct. Another important aspect here is that our neurons have some kind of state. The connection also has some kind of state, as I already said. But we differentiate the different classes, inhibitory, excitatory, and electrical. We also have in mind that connection has some kind of directionality. So we identify the dendritic connection to be these are incoming to a neuron, and the axon as the connection getting out of the neuron. Okay, now what is missing at this point is how to describe the behavior of a neuron. I mean, we need to define what happened in the output or the axon of a neuron that is having incoming stimulus from its dendritic connections. We call the neural dynamics to this description. In this work, we use three kinds of neural dynamics. The first is the well-known interrupted and fire, in which the neurons state are voltages. The dynamic is described by a differential equation like that, number one. And that equation describes the voltage with respect the voltage change with respect to the time. And we have other two equations that are modeling the behavior of the connections. In this model, we have CM, G-leak, V-leak as parameter to be learned in the neurons, and W and sigma as parameter in the connection. So we have in this network 85 parameters to be learned. Another neural dynamic model we use is named Isikievich, in which we have voltages also as a state. And the behavior is described in terms of the change of voltage in function of the time, with two ordinary equations like that, number 4, number 5. But we also have here an equation modeling spikes. So we have a model with a spike. The last two equations are modeling the connection between the neurons. And we have here A, B, C, and D, the parameters in the neuron, and W as parameter in the connections. So in this network, we have 76 parameters to be learned. By last, I proposed a neural dynamic model simpler than the others, trying to express the idea that something will happen on the axon only if the incoming stimulus is enough. Because of that, is present the parameter T, the threshold. But if not enough the stimulus, the only that can happen is the neuron tends to a quiet state. Because of that is the parameter decay factor. So in this model, the state is only a number without magnitude, nor physical or biological meaning. Once again, the connection are model depending on its type, as shown in the equation number 12. This model, besides its simplicity, shows advantages in terms of memory needs. Because of, for example, with respect to intermittent fire, this model has almost half parameters with respect to intermittent fire. And also in terms of computer times, the first models need to solve a differential equation each time is needed to execute the network. Meanwhile, that model only does simple arithmetical calculus like resting or adding amounts. These conditions makes this model to be 5 times quicker than the other. So this is another advantage. Now it's time to go to the second pillar. which is the environment. This piece has the same role as the classical reinforcement learning, so it implements the problems we want to solve. Works like black box, allowing us to execute a set of actions on it. Each time we execute one action, it gives us as a response some kind of state descriptor, a reward giving us a kind of measure of how successful was the action, and by last, a finalization signal, which is in charge of letting us know if the problem was solved or if we don't have more possibilities to execute action on the environment. Remember that in reinforcement learning, the sequence of interaction with the environment is that we call an episode. Okay, let's start with the problems we try to solve. The first is mountain car problem, or MCP for short. In this problem, we have a car between two hills, and as a goal, had to reach the flag. We can give to the car little impulses right and left to try to meet the goal. So the action in these problems are numbers in the continuous interval -1, 1, meaning left and right. The state descriptor has two values representing the car position and car velocity, and the episode finishes when the car touches the flag or when we interact 1,000 times without touching the flag. Then we have the second problem is the cart pole problem, or CPP for short. This is the second problem we try to solve. In this case, we have a cart with a pole near to vertical position. Where once again, we need to apply little impulses to the car in order to maintain as long as possible the pole between defining limits, impulses left and right. This time, the allowed action are only two numbers, 0 meaning left and 1 meaning right. The state descriptor has four variables in this problem, representing car position, car velocity, pole angle, and pole angular velocity. The episode finishes when the pole crosses the predefined limits or we interact 500 of time maintaining the polling position. The last pillar is the reinforcement learning agent, which is in charge of orchestrating all together. The reinforcement learning agent is who read the state provided by the environment and then translate it as appropriate and fits the proper network input neurons. After that, put the network to run, or in other words, to execute the simulation, the network simulation, and then read the output neurons states and translate it to an action understandable for the environment, and so on till the finalization signal arrives. So continue in this virtuous loop. On each episode step, the agent accumulates the rewards in order to select the episode with the best reward accumulation, and in fact, store the corresponding network. Once the episode finishes, the agent is in charge of selecting a new set of network parent values, and a new episode starts the execution of a fresh environment instance. We use three different well-known policies to pattern exploration, which are random-seq, genetic algorithm, and Bayesian optimization. Well, now you have the big picture. I'm going to introduce you to some of our results. We decided to test each trained model 1,000 times and use the result as a sample to get the statistics about the model being evaluated. We run lots of scenarios, depending on several factors, like the optimizer to be used, dynamic model, the amount of optimization steps, etc. So we have this amount of configuration for MCP and this amount of configuration for CPP. we collected start talking about the metrics and the MCP. We collected the mean reward of the sample because the consensus in reinforcement learning is to report the reward. But for us, was more significant report metrics that could give us some more information about how good the model is capable of solving the problem. So for MCP, we added two values beside the reward. Two values characterizing the steps the car reaches the goal. The first is the mean of a step, and the second is the minimum of a step it could do it. For CPP, happens something similar. We report rewards as expected, and also two other metrics related to steps. The first is also the mean of steps the car can reach the goal. And the second is the maximum steps the car can maintain the polling position. Well, now it's time. Here you have the 15 best models in terms of reward for MCP. The dotted line is showing the values appearing in the literature about this problem. Notice all our integrate and fire and few models crosses this line, so we get for both architecture very good results. In the second column of graph, you have the 15 best model with respect to the mean step for mountain car problem. Notice the best models are always few for both architectures. Remember, we are looking at the minimum value here. The third column contains the graph showing the minimum amount of step the problem was solved. We also get very good results. Here you have the reward report for CPP. Dotted line, this shows the success condition. I mean, the problem is considered solved when you get a mean of 119 steps in the polling position in one sample of 100 of tests. In the literature, the best results are close to 500 of steps like this. Notice we have a lot of internet and fire and few networks with mean reward of 500, like this, like this. This new graph shows the best model with respect to the mean of steps. Once again, we have a lot of networks with a mean of 500 steps, like this in both architecture. And the last column of graph shows the best models with respect to the maximum amount of steps the car can maintain the pole vertically. Notice the amount of models giving 500 as maximum, a lot of models. Due to the suspicious concurrence of models in these values, we decided to try to differentiate them and so defining a new version of CPP where we extend the 500 steps as a limit to 5,000 steps and retest to generate the samples and calculate the statistic of the model under observation. This new version, we call it extended CPP, ECPP for short. And well, we have here statistics for the 15 best models that are trained with an environment limit of 500, but were tested with an environment limit of 5,000. Notice internet few networks have mean step much bigger than 500, being some of them close to 1,000. This was very surprising result for us. Something similar occurs with the maximum steps. So, in conclusion, we experienced that this approach could be a viable alternative to conventional approach in order to solve reinforcement learning problems, getting very competitive results with a small size network. As future work, we can see to solve the problems using other techniques and collect our metrics for comparison. Maybe we can explore also in direction to different architecture and more advanced neural dynamics, and to explore the resolution of different problems, not just coming from the RL. For instance, quantum physics Well, that's all. I hope you could enjoy the talk. Thank you very much for your attention.
Thank you, Dr. Ariel. It was very interesting. Does anybody in the public has question? So I do have a question, Doctor. When
Okay.
you present the methods to perform optimization, for example, Bayesian approaches or genetic algorithms, are you optimizing the parameters of the network? I mean, the weights
Yeah.
of
Yep.
okay.
Yes. It's just looking for the best parameters that can reach the better reward or that the metric I am interested in. Yes, but it's just that are looking for the parameters that appears in the neural dynamics.
Some of the models have, for example, in a parameter, for example, of the neural dynamics graphs, their own parameters. Do you optimize them, or do you use a similar approach to optimize these parameters?
Sorry, I didn't understand the question. Could you repeat it?
Some of the I know that some of the models of neural dynamics has their own parameters. Do you manage? How do you manage to optimize them?
He refers.
Yeah,
Do you understand, Ariel? He refers to the parameter of the own parameter of the, for example, the random seek or we have many of them, and Isikievich, the internal parameter of that dynamic methods.
Clear. If I understand, let me see if I understand very well. That you are asking is how I manage the whole internal parameter. I mean, I have the networks in total, for example, for few model has 45 parameters. So the optimizers that is doing is just look at all these parameters. Not just in one neuron or one formula.
They are included as in the optimization methods is the answer. The parameters are included.
All right.
Yep.
Thank you. Thank you so much for your talk. It's very interesting. So let's continue with the final speaker.
Thank you very much, Fernando.
Goodbye.
Bye-bye.
Bye. Let's proceed with the final speaker. I think is Murat is Isik. Are you here?
Yes, I'm here.
Can you share your screen?
Sure.
So the final talk of this section is entitled as Design Optimization for High Performance Computing using FPGA. Dr. Murat is going to present. So please, Murat, you can present.
Thank you so much. First of all, I would like to highlight that I'm not a doctor yet. I'm a PhD student at Stanford University. And today I'm excited to talk about the critical role of the five programmable gate arrays in enhancing high performance computing. Specifically, we will delve into the FPGA design optimization, significantly advance real-time vision-based machine learning inference. So here is my presentation layout, and I will be following through this layout of my presentation. And we will start by examining the challenges faced in machine vision frameworks, explore the FPGA solutions can address these challenges. Then I will talk about our methodology and the impactful of the results which we achieved. So, as you know, real-time vision-based motion tracking is quite important in the different range of the application, from the advanced surveillance systems to intelligent traffic control. And the essence of these applications lies in their need for speed and computational efficiency, where traditional computing methods often fall short. So here, I'm trying to show that what type of challenges we have in machine vision framework. So implementing the machine vision frameworks comes with its own set of challenges, primarily around the processing speed and adaptability. So here is where FPGA comes into the play and offering the configurability and parallelism necessary for these throughput applications. So go to the first little presentation here. Let's talk about the critical role of the image processing in various domains and how high-performance computing systems, especially those built around the FPGAs, are game changers due to their parallel processing capabilities and energy-efficient architecture. And as you see here, we are mentioning the four main blocks: resolution and the image size, real-time processing, complex algorithm, and parallel processing. So here is the challenges in adopting for FPGA, challenges in adopting FPGAs for high-performance computing. And FPGAs have a long history in various applications. It has been developed cost, complexity, and expensive tool and technologies, and limited availability of the high-level software tools and the need for deep hardware understanding. But however, the benefits far outweigh these obstacles. So, okay, fortunately, recent developments are making FPGAs more accessible, and tools for high-level synthesis and growing library of the previewed IP blocks are simplifying FPGA programming, paving the way for broader adaptation. So, yeah, we are mentioning the three main recent developments here. And then, okay, what are the current open source ML inference accelerators? And what is their advantage here? And I will describe the integration of the machine learning inference in high performance computing. So machine learning inference is critical for analyzing input data and generating output results in many modern applications. So the VTA, Versatile Tensor Accelerator, is the first open source ML inference accelerator gaining the significant attention. It supports the popular frameworks like TensorFlow, PyTorch, and ONNX across the various hardware platforms, making it a versatile choice for the developers. So, okay, what are their benefits and advantages? And open source machine learning inference accelerators are specialized hardware devices, are designed more efficient ML inference. And while GPUs are widely recognized in high performance computing for ML inference, we now seeing the emergence of the new technologies such as FPGA and ASIC architectures. Okay, right now we have the two open source machine learning accelerators such as Nego and Tensor AI. So Nego is focusing more large scale neural network, but Tensor AI, which we use it in our paper, is focusing the accelerating the machine learning inference task. Instead of making it really big, they are trying to make it more optimized architectures. So here we have the three main topics, and we would like to highlight what type of use case we have like low latency ML inference in applications like self-driving cars, or if you simulate like a larger neural network, Nango will be the best choice for you. Then we are talking. So here I wanted to mention what is the drawback of the Tensor AI. Of course, it has a limited flexibility due to the specialized hardware nature, and previewed models and architectures might be required too. So yeah. And the next slide. Okay, here we are. I'm talking about our approach involved proposing Vivoda hardware design, Xilinx URAM, and advanced compile strategies. So these elements were critical in optimizing the performance of our systems, and we focused on ResNet 20 optimization on the Xilinx Zinc UltraScale 104 using the Tensor AI open source accelerator. So here is the key thing is our method is post-training optimizations, and techniques like pruning reduce the computational load, while quantization with the Tensor RT achieves 8-bit precision, conserving memory and resources here. And of course, I will cover what are the results and differences based on the baseline design. So, okay. Here we started with a baseline design using the 32 cross 32 systolic array for high DSP unit utilization, and then maximize the memory usage, like pushing the VRAM to its limitation. Then we leverage the Zinc UltraScale's SD card interface for the data access, utilizing the Tensor AI's embedded driver file system for reading the ResNet model and Cipher10 test set. And for the first baseline design, we achieved 133.54 frame per second, and accuracy was quite normalized around to 90%, with a 2% drop attributed due to the bit conversion, 32-bit floating point to 16-bit fixed point. So, okay. Then we made the dual clock solution, and we introduced it to like a 333 megahertz clock for Tensor Xi ports and widened ports for enhanced conversion rates. And this dual clock solution led us to give 152 frame per second. Here I can put it, yes, here. And 152 frame per second. And we tried to focus the optimizing the data and control the paths into the accelerated design, operationing the data in a higher frequency for increasing the throughput. So then, okay. And our approach included optimizing the memory access here, and these high density, low latency memory blocks are feature of the Xilinx FPGAs. And in our ResNet application, URAMs were used to store the neural network model weights, supporting the concurrent reads and writes to enhance the performance. So I'm trying to catch the time, so making it a bit faster. So the use of the URAM solution significantly improved our performance achieved, and we got to 170 frame per FPS. So this optimization allowed for larger on-chip memory, reducing the partitioning and enhancing the data flow efficiency and loading the speed. So here is our compiler strategy with the large local memory. And our strategy focused to enhancing the speed and latency of the local memory resources in FPGA, such as VRAM and URAM. And then we utilize the data weights stored in local memory for speed and reduce the latency, implementing techniques like weight compression and quantization. So Tensile AI compile strategy was adopted for large local memory, assuming the sufficient local memory weights, inputs and output activations, particularly beneficial for small to medium-sized FPGAs on large FPGA devices. So the final optimization was here. The final optimization was focusing the Tensile AI architectures, supporting the URAM, and we wanted to make it like a first layer to last layer within the proposed compile strategy for optimizing the local memory. Okay, what are the results? And results were quite promising for us. Our results show that FPGA was quite power efficient, energy efficient comparing to others, such as Intel and CPU and GPU. So we wanted to see that what are the out performance over the different hardware devices. So then we made the comparison between our accelerators to state-of-art implementations, and we observed the significant improvements in power efficiency and throughput, especially with the Tensile AI inference accelerator. Okay, here I'm trying to show that what was the FPS increasing within the single solutions. Like we started 133 megahertz of FPS, and then lastly we achieved like a 298 frame per second end of the design. And here we are showing the three main steps, like what are the performance improvements for us and research hotspot and figure highlight. So we demonstrated the improvements in Vivado hardware design, and we leveraged the Xilinx URAM and advanced the compile strategies for the interface inference performance. And two things we were focusing here: we developed the FPGA-based hardware system for neural network inference, and then we aim to achieve the high throughput and power efficiency. And of course, we wanted to show the and we wanted to present what are the image processing difference for each section. Okay, in conclusion, our study demonstrates the feasibility and the effectiveness of using the FPGAs for accelerating the machine learning task. Looking ahead, we are excited to explore the dynamic partial reconfiguration and develop the high performance frameworks further. So, yeah, thank you so much for listening to me. If you have any question, I would love to answer.
Thank you, Murat Isik, for your presentation. Is there any question for the public? Okay, I think it was very clear.
Sorry, I have a question. Sorry.
Yes.
Yeah.
Thank you so much, Murat. Do you have some new avenues for your project, for your work?
For me?
Yes, for your work. Do you have some new future works, next steps in your work?
Yes, actually, we wanted to use the we would like to use the dynamic partial reconfiguration to partial our neural networks, because right now we are working with the quite larger spiking neural networks, and we believe that if we try to partial them and try to make it how can I say reconfigurable, then we can get some achieve points for our design. But of course, it was just one idea, and another idea will develop our own open source machine learning accelerators. But still, we are, how can I say, we are trying to find the correct scope to do it, because we need to have some novelty. Yeah, like Tensile AI and Nengo are mostly okay. Tensile AI is the open source work, and it's not related with the company, but Nengo is a company software, and actually they have a team and budget for that. So we are not sure for the our own open source machine learning accelerator, but we will definitely focus to dynamic partial reconfiguration to make it like a better.
Okay, thank you so much.
Yeah. Okay.
Thank you, Murat Isik, for your presentation.
Thank you so much, Bernard.
The next speaker is Dr. Stefano Ermon from Stanford University. He's not here. We're going to wait for him.
Yeah, exactly. He just sent an email.
Yeah, he's in the waiting room.
Yeah, exactly. I don't know if you will present Stefan or maybe me as you want, Professor Aguilar.
If you prefer, you can present the speaker.
Okay. Okay, I think that Professor Ermon is here. Hello, Professor Ermon. Professor Ermon. Good morning, Professor Ermon.
Good morning.
Good morning. Thank you so much for being here. Hello.
Hi. Can you hear me okay?
Yeah. Sorry for my last email. Sorry, I'm really sorry. So it's me that I will introduce you. So it's for SIMBig a pleasure. It's for me a pleasure to introduce Professor Stefano Ermon. Professor Ermon is an associate professor in the Department of Computer Science at Stanford University. He is affiliated with the Artificial Intelligence Lab. He is also a fellow of the Woods Institute of the Environment. His research is in the machine learning and generative artificial intelligence. He likes to develop principled methods motivated by concrete real-world applications and problems of broad societal relevance. Professor Ermon, welcome to SIMBig. Thank you so much for help us with the Latin American community of computer scientists. Thank you so much for being here.
Thank you. Thank you so much for the introduction. And yeah, my pleasure to be here. And today I'll be presenting some of the work we've been doing around the diffusion models. So just as a background, you probably all seen there's been a lot of progress in generative AI, of course, the various GPT models, lots of excitement around generative models of text. But I think there's been an equally astounding amount of progress in computer programs, generative models that can create images, for example, based on captions. So now we have systems like Stable Diffusion, DALL-E 2, DALL-E 3, where you can input a caption, something like this, in a fantastical setting, highly detailed furry humanoid skunk with piercing eyes, confidently poses in a medium shot, wearing an animal hide jacket. And you can get the machine to generate an image corresponding to this caption, and you can get results that look like this. This is from a recent diffusion model that we developed. So extremely detailed, very realistic, very matches very well the kind of like description provided in the caption, and it really demonstrates some incredible capability in terms of like combining different kinds of concepts. Right, this is probably not something the algorithm or the model has seen before, but you know, it has seen a skunk, it knows what a leather jacket is, and it's able to combine all these concepts in a meaningful way. Here is another example that I like. A swirling multicolored portal emerges from the depths of an ocean of coffee, with base of the rich liquid gently rippling outward. And you can get the model to generate an image, and you can try to imagine what something like this should look like. And you know, with again the model I described before, we can get results that look like this. So again, very high quality images that kind of correspond to the provided caption. Now, these kind of models, they can be prompted not just using captions, but also using, let's say, sketches. Here's an example of kind of results we can get when you provide the system a sketch, something that even I could produce on the left, and you can ask the model to produce a pretty picture that is kind of like consistent with the sketch provided by the user. And you can see some of the results you can get. And you can see how it preserves the structure. There's the little river and the grass, and but the images look very beautiful. They're very, very artistic. Now, at the core of these generative models is essentially a very basic type of statistical model, which is essentially a probability distribution over the space of possible images. So the underlying assumption is that there is a data distribution of natural images. You can think of it as some kind of like function that assigns a probability value to every possible assignment of pixel values. And this distribution is unknown. The only thing we have access to is a bunch of samples collected from the internet. And at the core of these really exciting generative models is a distribution, a model that is trying to approximate this unknown data distribution. And the reason this is important is that once you have this model distribution, you have access to this function that will tell you for every possible image, how likely is this configuration of pixel values, then you can use it to sample from it. You can pick points in this space. Of course, the real space is much higher dimensional than this two-dimensional toy example that I'm showing here. But you can kind of like pick points in this space that are likely under the curve, and that will generate new data points that hopefully have the right structure if you've learned the model sufficiently accurate. And that's the generative model at the end of the day. It's a very basic kind of statistical problem where we are just trying to estimate a probability density function from data. Now, the real challenge is that this unknown data distribution is very complex. And so the core problem is, how do you come up with sufficiently complex models for this probability distribution? And before diffusion models, the most successful approach was based on generative adversarial networks or implicit generative models, where instead of representing the probability density function, we represent directly the sampling procedure. So we can take a random noise, feed it through a neural network, and train the parameters of the neural network, so that this sampling process produces images that, let's say, look like the ones in the training set. The advantage is that this is a very flexible kind of architecture, because any architecture defines a valid sampling procedure, and it worked reasonably well. But it's pretty unstable because we no longer have access to a probability density function. So given an output image, we cannot evaluate easily how likely was the model to produce that particular sample. So it's difficult to train these models. It's difficult to compare whether model A is better than model B. And so it's much easier to work with the explicit models, where we directly represent this probability density or probability mass function. And this is a problem that has been studied for a long time. There's a lot of classic approaches based on graphical models, Bayesian networks, autoregressive models, flow models. The key advantage is that we have access to probability values. The problem is that it's not easy to actually come up with sufficiently rich model families that can actually capture the complexity of a real-world data distribution. And so the real-world data distributions that we're trying to model are very complex. They have many modes. There is many regions that should be assigned very low probabilities, regions that should be assigned high probability, and figuring out what is the right shape of this distribution is very complex. And so how do we come up with a sufficiently rich class of model distributions that can approximate this, the complexity of a real world data generating process? And we all know how to build simple model, statistical models. For example, a Gaussian distribution, that is a valid probabilistic model. You can think of it as a very simple, very shallow kind of like neural network. It takes as input a vector of pixel values and maps it to a scalar, which is the probability assigned to the input x, according to the usual Gaussian PDF kind of formula that you see here. And this is a great model. It's very useful in a lot of different applications, but you can see that it's kind of like too simple. It's unimodal. It's putting all the probability mass around a single kind of point, and it's never going to capture the complexities of a real world data distribution. And so naturally, the idea would be, well, let's use deep learning. Let's use a deep neural network to represent this function that maps, say, images to probability values. And that's kind of like the key idea behind deep generative models. Use deep neural networks to represent probability density functions or probability mass functions. However, it's not as straightforward as it might seem. And the reason is that if you take an arbitrary neural network, the output that you get might even be negative, right? And we know probability values have to be non-negative. They have to sum to 1. And so an arbitrary neural network will not define a valid probabilistic model. Making sure that the outputs are non-negative is pretty easy. You can take an arbitrary neural network, you can apply a non-linearity like an exponentiation, and the resulting neural network will output non-negative values. That's easy. The much more challenging part is to make sure that if you integrate over all possible inputs, you get 1. And in order to do that, you basically have to divide by this normalization constant that I've denoted here with z theta. And that's just the integral of the unnormalized probability over the whole space. And in the case of a Gaussian distribution, it's that term that you have in the denominator, and it's easy to compute. But if you have an arbitrary neural network, this quantity involves a very high dimensional integral, which could have hundreds of thousands, millions of dimensions, and it's very hard to evaluate. And in fact, it's probably hard to compute this for many classes of functions. And there's been a lot of work in statistical physics. Lots of smart people have thought about how to approximate this quantity, because it's a very important quantity in when you're modeling physical systems. So this normalization constraint is kind of like the main reason we cannot choose arbitrary neural networks, and we have to always make some kind of trade-off between how flexible the neural network is and making sure that we can still tractably essentially evaluate the normalization constant. Now, the reason diffusion models are so successful is that they allow us to bypass this normalization constant. And the idea is that if you are modeling probability density functions directly, which is the typical thing we do when we build statistical models, you kind of have to define functions such that you can change the parameters, but they are normalized. You can move around probability mass, but the total area under the curve has to be 1. And if you want to use a deep neural network to model this, then you have to essentially, if you pick an arbitrary function that doesn't integrate to 1, you have to divide by the area under the curve to get 1, and that involves the partition function or normalization constant, which is hard to evaluate. Now, the key intuition behind the diffusion models or score-based models is that we can work with the score function, which is just the gradient of the log of the function you see on the left, and use that as our key object of interest. And the reason we do that is that the score function is much easier to work with. And so in particular, if you take the log of the expression on the left, and then you take the gradient with respect to x, which in this case is just the derivative of the function you see on the left is the score, which you see on the right. And you basically get two terms. And the key thing to note is that this log partition function does not depend on x. And so whenever you do take a gradient with respect to x of that constant, you get 0. And so you can see that the moment we look at the score, the normalization constant disappears. And so the key idea behind diffusion models is to directly model the quantity we have on the right, the score, instead of modeling the density function itself, which we have on the left. And that's a score model. That's kind of like the key underlying object that we use in diffusion models. Now, just to summarize what we discussed so far, typically people work with probability density functions, and instead we're proposing here to work with the score function, which is just the gradient of the log. And so intuitively, you can think of the probability density function as being, the scalar function that maps points to probability values. Here I'm showing you the probability density function corresponding to a mixture of two Gaussians, one on the top right corner, one on the bottom left. You can see, here, red values correspond to high probability density values. The corresponding score function is a vector field of gradients. At every point, it gives you the derivative of the log of that expression. And so that's just an arrow that is basically pointing in the direction that you should follow if you want the log density function to grow as rapidly as possible. It's just the definition of a gradient. So the score is basically all the arrows that you see in the plot that are kind of like pointing towards these regions of high probability, the modes of the original density function P of x. And these two quantities are somewhat, they're to some extent equivalent, but we'll see that working with the score function has many computational advantages. So in particular, it turns out the score models can be estimated directly from data. So if we have training data, just usual IID samples from some unknown data distribution, we know how to fit probability density models. You just choose the parameters data that maximize the probability of the training data or the maximum likelihood. That's well understood. The question is, how do we fit a score model to data? If you only have data, how do you figure out how to choose the direction of the arrows so that they match the true vector field of scores corresponding to the unknown data density when the only thing you have access to are samples? So you get to see a lot of data points, a lot of blue dots in regions of high probability, very few data points in regions of low probability. So more formally, how do we do this? There is an unknown data density. We get to see a bunch of samples from it. How do we estimate a vector field of scores that is accurate? It's close to the true vector field of scores of the data distribution. So mathematically, the problem is as follows. We're given a set of IID samples from the data distribution, and the goal is to estimate the score function of the data. We're going to consider a score model, which is, think of it as a neural network, parameterized by theta. It's a vector valued function. It takes a vector as an input and has a vector output. Same number of dimensions in the input and the output. Here, D is the dimensionality of the data. And we want to choose parameters theta so that this function is as close as possible to the true vector field of scores. How do we compare two vector field of scores? There is a true vector field of scores corresponding to the data distribution. There is an estimated vector field of scores. What we can do is we can overlap them. At every point, there's going to be a true score, true gradient, an estimated gradient. We can look at the difference. And if these vectors of differences are small, then we have a pretty good model. And one way to quantify this is to just look at the norm of all of these error vectors and average them. And that will give us a scalar value that tells us, on average, how far off are we from the true vector field of scores. And mathematically, this is the Fisher divergence. You see the mathematical formula here. So it's an expectation with respect to the data distribution of the difference of the norm of the difference between the true score and the estimated score evaluated at X. And you can see that if this quantity is 0, then it means that we've matched the score of the data distribution exactly, so that's great. However, it might seem like it's a quantity that it's going to be impossible to evaluate and optimize as a function of theta, because the score of the data distribution is unknown. Recall, the only thing we have access to are a bunch of samples, and we don't know what p data looks like. Otherwise, it would be done. Turns out that if you do integration by parts, you can rewrite this objective function into one that is equivalent up to a constant, and it no longer depends on the data distribution or on the density or the true score of the data distribution. You can see the expression at the bottom only depends on S theta, which is our model. Not super important to understand what it means, but there is a way to rewrite this objective into one that can be evaluated, can be optimized as a function of theta, and can be approximated basically using samples. So we approximate the expectation with respect to the data distribution with a sample average. And so all you have to do is to basically choose values of theta such that the objective function at the bottom is as small as possible. And it's an objective function that kind of like makes sense. We're saying that we're trying to choose values of theta such that the estimated score evaluated at the data points is small. That's kind of like what the first term is saying. So we want to make the data points stationary points for the vector field of gradients that we're estimating. And the second term is essentially trying to change the curvature at the data points. And it's trying to make sure that the data points are essentially local maxima instead of local minima of the underlying density. And that this objective function can be optimized as a function of theta, and it can be used to basically estimate a vector field of scores from data. Now, the question is, once we've done this, how do we actually generate new data points, right? If all you have access to is a bunch of score functions, how do we, how do we use this information to generate new data points? At the end of the day, that's what we care about. That's what we're building a generative model for. And the intuition is that this score function is kind of like telling us in which direction we should, if you have a suboptimal kind of solution to the problem, if you were to follow the arrows, you could improve the quality of your sample by moving it towards regions of higher probability. You can imagine a procedure where you initialize a bunch of images, each one corresponding to a blue dot in this toy kind of example, and you perturb these images by following the scores. Kind of like try to move them towards higher probability regions. And this kind of like makes sense. It's not quite right. It's not a quite valid sampling scheme, but a small modification of this called Langevin dynamics is actually a valid sampling procedure for this model. So all you have to do is you follow the arrows and you add a little bit of noise at every step. And if you do that, you get, if you repeat this process for a sufficiently long amount of time, you get a valid sample from the density whose score you've estimated using this score model. And so, although in theory this works, in practice, if you try to fit this model on, let's say, CIFAR10, you see the samples on the left. You fit a score model, you run Langevin dynamics, you're going to see the results, the images that you see on the right, meaning that this model doesn't work at all. And this has been a challenge for a number of years. And the reason kind of like this doesn't work is that if you think about it, the training objective looks like the formula we have above. And we are approximating the expectation with respect to the data distribution with a sample average. And kind of like most of our data points are coming from regions of high probability. And so we're kind of like locally estimating the scores when we are already close to high probability regions. But if you think about the Langevin dynamics procedure I talked about, at the beginning, we're going to start with very poor quality samples that we have not seen during training. So we're not going to get good directional information for improving the quality of our samples. And so the Langevin dynamics procedure gets lost is not able to find high probability regions, and that's why the samples were not good. And so the solution is to basically add noise to the data. If we add noise to the data, we get a new perturbed density that is kind of like covering the whole space. It's much more spread out. And it turns out that if we apply score matching to this perturbed density, we can estimate the scores much more accurately throughout the entire space, not just close to the high probability regions, but all over the ambient space. So high noise provides useful Langevin dynamics information. However, if we add noise to the data, we're no longer modeling the true data density, but we're modeling data density perturbed with noise. So the solution is to consider multiple noise levels. So we're considering a variety of kind of noise levels, sigma 1, sigma 2, and so forth. And you can think of it as increasingly large amounts of noise that we add to the data. And what we do is we jointly estimate the scores of all these data density perturbed with increasingly large amounts of noise. So we have a single noise conditional score model that takes as input X, the noise level sigma, and estimates the score for the data density perturbed with noise intensity sigma. And we just train it using the regular score matching objective that I talked about before. And what happens now is that once we've estimated all the scores, we can use a procedure called annealed Langevin dynamics, where at the beginning, we use the score information corresponding to the data density plus a large amount of noise. Then we use these particles to initialize the Langevin chain, where we follow the gradients corresponding to the data density with a smaller amount of noise. And then we keep annealing the amount of noise that we add until at the end, we're sampling from a distribution that is very close to the original data density, because sigma 1 is extremely small, the noise level sigma 1. And this procedure actually works. And here you can see a demo of how it works. And you can see how, if we train the score model on MNIST, CIFAR10, and so forth, and then you run this annealed Langevin dynamics procedure, we get this process where we start from pure noise. You're going to see soon when it loops back here, it starts from pure noise, and then it slowly kind of removes noise from the images and turns them into clean samples. By essentially following the directions, following the gradients estimated by the score models. And this is really the key underlying sort of technology behind diffusion models. When we initially used this model, we were able to get state-of-the-art results on CIFAR10 back in 2020. Bands were state-of-the-art, and even though people have spent years kind of like engineering good solutions for GANs, using this approach, we were actually able to achieve better sample quality as measured by FID score, conception score. It's not super important that you know what they mean, but these are just metrics that quantify how good the images look like. And this was super exciting because for the first time, we were able to design a new generative model that was able to beat GANs, which had dominated the landscape of generative models of images for many years. And after we did this, technology that is behind Stable Diffusion, Google Imagen, DALL-E from OpenAI, Journey, and many other kind of state-of-the-art image generation system. Now, more specifically, these models are called diffusion models because you can think of them as models that essentially are able to transform noise into data. So we can think of this as there is a process that goes from data to noise. And we can think of this process as, and we can describe the process using a relatively simple stochastic differential equation. And not super important to understand the math here, but it's describing this process, which is actually a diffusion process that takes data and turns it into noise by adding small amounts of infinitesimal noise at every time step. So you can see here that there is an initial data distribution P0, which is a mixture of two Gaussians. And you can see that as we add more and more noise to the data, we're transforming this distribution into one that is pure noise, corresponding to PT. And what we do in a model or a score-based model is we try to reverse this. We try to go from noise to data. And turns out that if you flip the direction of time, we have this forward stochastic differential equation that just adds noise. This is essentially some kind of continuous type random walk. It turns out that if you reverse the direction of time, this is just a change of variable. You get another stochastic differential equation that describes the process of going from noise to data. And we know exactly what the functional form of this stochastic differential equation is. You see it here. The important bit is that it depends on the score function. So if you have access to the score function of all these different data densities with increasingly large amounts of noise, then you can reverse this stochastic differential equation. And by solving a stochastic differential equation, you can generate new samples. And this is exciting for a couple of reasons. I think the most interesting one is that it allows us to leverage decades of numerical methods for solving differential equations of various kinds to generate samples very, very efficiently. So in particular, it's possible to actually convert this stochastic differential equation to an ordinary differential equation. So we have this stochastic differential equation. There's an equivalent ordinary differential equation that defines different kinds of stochastic process, where the randomness is just in the initial condition, and then the dynamics are completely deterministic. But at every step of the way, these two processes, the stochastic differential equation on the left and the ordinary differential equation on the right, they define exactly the same marginal distributions. And this is exciting because we know how to solve ordinary differential equations pretty well. Again, this is a complicated kind of ordinary differential equation because, once again, it depends on the score function. But if you plug in our score model, score function that we've trained using score matching, we can then attempt to solve the ordinary differential equation and generate samples by essentially using advanced numerical methods. So, in particular, there is a lot of exciting progress in generating samples very efficiently. While if you were to solve the stochastic differential equation, it might take maybe 1,000 kind of like discrete steps to generate it. Using advanced numerical methods, it's actually possible to essentially use a fairly coarse description of the time and essentially take big steps to go from noise to data. And so what we were able to do is, by leveraging some of the mathematical structure of the underlying ordinary differential equation, it's possible to use this kind of advanced integration schemes for ODEs that will essentially give us roughly the same sample quality. So you can generate images of high accuracy, but much faster, maybe 10 times, 50 times faster, which is exciting because that drastically increases the quality of the user experience with this kind of systems, because you don't have to wait 10 minutes to generate an image. Maybe you can get it in a minute or 30 seconds or something like that, which is much better from a user experience point of view. The other kind of clever approach that is getting a lot of traction is based on distillation. And the basic idea is that, as usual, there is this underlying ODE, which is very, very important in a lot of these acceleration schemes. And we have this, DDIM kind of, which is the method I just talked about before, which is just some way of solving the ODE up to some accuracy and get images at the end. Now, it turns out that we can use the DDIM model as a teacher model, and we can train another neural network, student model, that tries to do what the teacher does in 2 steps but the student does it in one step. So you can see here that the student is able to jump in one step over 2 steps of the teacher model. And if you can train the student model to do what the teacher does in 2 steps, in 1 step, then you've reduced the runtime in half. And what they do is then they apply this idea recursively. So once you have a good student model, then you train another student model that tries to do in 1 step what the previous student model did in 2 steps. So now you do in 1 step what the original teacher model did in 4 steps. And you can see that if you can really do this well, you can, again, drastically reduce the number of steps required to generate samples. And here are some of the examples you get using this technique that we presented at CVPR last year. And you can see that we were able to distill down a stable diffusion generative model into one that can produce images in 2 steps, or 4 steps, or 8 steps. So you just basically need to follow the gradient 2 times or 4 times, and you can generate high quality images that are hard to distinguish from the original ones. And people at Stability AI have actually further improved this technique, and now they have a system that can actually generate images in a single step. So extremely efficient. They've gotten pretty close to real-time generation. You can type a caption, and the system can generate an image essentially in real time, which is, of course, very exciting in a lot of applications where latency is super important. Another technique that we actually just presented at NeurIPS this week is based on leveraging so-called parallel in time integration schemes to compute solutions of ODEs very efficiently. So imagine that what we're trying to compute is this blue line, which kind of corresponds to the solution of this ordinary differential equation that maps noise to data. And the traditional way of doing it would be to sequentially basically integrate the ordinary differential equation by computing the gradient at every step and kind of computing the trajectory step by step from left to right. That's the brown kind of particle that you see there, which might take maybe 1,000 steps to really go from noise to the clean data corresponding to that initial noise sample. And again, that's too slow. We don't want to wait that long to actually generate images. So what we can do is we can try to compute the trajectory in parallel. So if you have access to multiple GPUs, or somehow your GPU is underutilized and you have more flops that you can kind of like take advantage of, what you can do is you can try to do what the blue dots are showing here, where essentially multiple segments of the solution of the ordinary differential equation are computed in parallel. And there's a class of numerical ODE solvers called parallel in time ODE solvers that are essentially leveraging this idea of computing the solution of the ODE in parallel across time. And these methods can be very good at basically leveraging parallel compute and reducing the wall clock time. So this is kind of like a technique that actually computes the exact same solution of the original sampler. So there's no loss in accuracy. But if you can actually throw more compute, you can throw more GPUs at it, you can do it faster. Even though the initial computation kind of looked very sequential, it looked like a kind of computation where there is nothing you can do to accelerate sort of like the computational process. And you really have to go from left to right to get the full solution of the ODE. Turns out that using these techniques like Picard sampling or parallel, there is a number of parallel in time algorithms that can be used, and they can drastically accelerate the time that is required to get a high quality solution. You can see the blue curve. You can see how it converges very quickly to that image of that castle that you see on the right. And more recently, we've generalized this idea to kind of like arbitrary computation graphs. So we've applied these ideas to 3D generative models. Here is a cool kind of like demo showing the process of going from an image to a 3D model of that image. And you can see kind of like the original computation on the left that might take maybe 6 minutes versus our computation that does things in parallel, which does the same, gets you the same result in only 1 minute. And you can also do this to accelerate text to 3D models. So there are these models that people have developed also based on diffusion that would say, take a caption, like a detailed Victorian era house, and would generate a 3D model corresponding to that caption. And again, these models are typically very slow. They involve very long kind of sequential processes that are very expensive to evaluate and unroll. Oops. And you can see kind of like the difference between what people typically do, which is the model you see on the left, where it takes a lot of time to kind of like diffuse noise into the 3D model of the house. It might take maybe 5 hours to generate this house that you see on the left. And using our parallel compute, we can basically get the same result in 54 minutes. So again, it's kind of like a natural generalization of the idea I talked about before to different kinds of computational graphs, different kinds of ODEs that correspond to other kinds of generative modeling. So pretty exciting opportunities for bringing in relatively old ideas from numerical methods, from clever techniques for integrating ODEs, and give it a deep learning twist and use them for the latest kind of generative AI applications. Let me see. Okay, so I have a little bit of time to talk about how you can use diffusion models to also control the generation process. So let's say that you train a model to generate images from some distribution P of X, which for this toy example, let's say contains images of cats and dogs. Now let's say that you want to control the generation process and you want to generate an image of a dog. So if you have access to a classifier that takes an image X and tells you how likely it is that this image corresponds to the class dog, what you really want is to basically sample from the posterior distribution over images X, given that the label Y is the one of a dog. So you can see that incorporating this forward model or this likelihood changes the shape of the distribution over images, putting more probability mass on images X that are going to be classified as a dog by this forward model P of Y given X. And so if somebody gives you P of X, somebody gives you a classifier that classifies images into different classes, then in theory, by sampling from P of X given Y, you can control the generation process and you can get the model to output images that are consistent with some kind of control signal or label that is provided by the user. And this inverse distribution can actually be computed from Bayes' rule. Like this is the classic kind of rule that you've seen probably in many undergrad courses, where we can compute the posterior distribution by multiplying the prior with the likelihood and then normalizing by this marginal distribution over the label Y in the denominator. And that, again, the denominator is the thing you need to divide for in order to get a normalized probability distribution. It's identical to the partition function, the normalization constant that we were talking about initially. This P of Y is just a constant that does not depend on X, but you need it to make sure that if you integrate over all X's, P of X given Y will give you 1, which is the what we want from a probability density function. It has to be normalized. And Bayesian statistics, Bayes' rule is great. It's very powerful. It tells you what's the right way of combining prior information with evidence or likelihood to get a posterior distribution. And it's optimal in a number of ways. The problem is that it's computationally very expensive because computing the normalization constant, once again, is very challenging from a computational point of view. But again, we can see that working with score functions is not only good because of model inflexibility, it's not only good because it allows us to use ODEs, SDEs, and fancy numerical methods to accelerate sampling, but it also allows us to control the generation process very effectively. And the idea is that if you look at what this Bayes rule will tell us about the relationship between the score functions, so you just take a log of the expression on the top, and then you apply it, you compute the gradient with respect to x, that quantity. Once again, we see that the term that we didn't know how to deal with, that p of y, does not depend on x. And so the moment we take a gradient with respect to x to compute the score, that term disappears. So what this is telling us is that doing Bayes statistics or Bayes kind of updates, working with scores, is very efficient, because the only thing you have to do is to do addition. So if you want to get the score of the posterior, all you have to do is you have to take the score of the prior, which could be a pre-trained generative model over images. You combine it with the score of the likelihood, and the combination is very simple. Just add them up, and that gives you the score of the posterior distribution. And so what this means is that if you have a good pre-trained model, let's say over images as data, you can combine it with any p of y given x, and you can use it to kind of control the generation process in many different ways without having to retrain the model in any way. And so, for example, the kind of examples I was showing you before of using a stroke painting to control the generation process and getting the model to generate an image X that is likely under the prior but is close to the stroke painting can be seen as some kind of inverse problem, where what we want to do is we want to condition on the stroke painting Y, and we want to sample from P of X given Y. And in this case, P of Y given X can be specified by hand, so we can get the score of that, combine it with the score of the prior, and these are the results that you get. And in fact, this is exactly how we got this sort of like very pretty result I showed you before. You start with a good generative model of natural images, you combine it with a likelihood function that forces the model to output images that are not only likely under the prior, but they're also consistent, in this case, with the sketch provided by the user. And this is how we get this kind of amazing controllable generation sort of results. And conceptually, that's also how you do language-guided generation. So if you want to control the generative process using captions, so now Y is no longer a label, it's no longer a sketch, Y is a caption. As long as you have some kind of image captioning model that will tell you how consistent is Y, the caption provided by the user, with an image X, then you can use this forward model, this likelihood, you can combine it with the prior, and you can do language-guided generation. It turns out that you can also use this kind of technique to solve inverse problems in medical images. In this case, this is a really cool application of score-based models where we were looking at MRIs or CT scans. Here, the conditioning signal is no longer a caption, it's no longer a sketch, but it's the actual measurement that you get from the MRI machine. And what you want to do is you want to infer what is the actual cross-sectional image of the patient's body given the measurement obtained from the MRI machine or the CT scan machine. And ideally, you want to do it, you want to be able to infer what's going on inside the body of the patient using as fewer measurements as possible. You want to use the least amount of radiation possible and still be able to reconstruct an accurate view of what's going on inside the body. And intuitively, if you have a good model, a good generative model of what medical images look like, so you have a good prior over what natural images look like, you might be able to drastically reduce the number of measurements that you need to get in order to reconstruct an image X that is consistent with the measurement that we obtain for this particular patient. And indeed, in this case, P of Y given X is given by the physical simulation of the CT scan machine or the MRI machine. And we have a prior model of medical images, and we can use it to do medical image reconstruction. And I'll go quickly through this because we're running out of time, but what I'll say is that this kind of a plug and play approach where you take a score-based diffusion model over medical images, you combine it with your knowledge of how an MRI machine works, the relationship actually outperforms bespoke solutions that people had developed before, including ones based on deep learning that people were using to reconstruct medical images in CT scans and similar in MRI kind of images. So there's a lot of applications of this kind of good generative models of images, not only for natural images and arts and media, but also in the physical sciences, in engineering, medicine. Lots of exciting applications of these ideas. So yeah, I think it's time to conclude. So the kind of main takeaways is that when building probabilistic models, working with score functions is very effective, because score functions can be don't have to be normalized. So you can choose an arbitrary neural network to model the score function, and they can still be estimated from data, even though you can no longer do maximum likelihood training. You can use score matching, which is a proper scoring rule, has a lot of good properties. It's very stable during training, and this is one of the key reasons for the success of these models in practice. We no longer have to rely on very unstable minimax optimization that you would have to use for training a generative adversarial network, for example. It's a very principled kind of training objective that actually works in practice and scales very well. Turns out that if you really wanted to, there is a way to do maximum likelihood training. I didn't cover it in this talk, but through the ODE perspective, it's also possible to compute likelihoods exactly according to these models. It's also possible to show that there are some connections between score matching, maximum likelihood, and under some conditions, it's possible to approximately train the models for maximum likelihood if you cared about that. So you wanted to do compression, then you might care about likelihoods, and it turns out we can also achieve very competitive likelihood scores using score-based generative models. These kind of models achieve state-of-the-art sample quality. They've led to massive success in systems that are widely deployed in industry, now used by millions of people all over the world. One nice thing about these kinds of generative models is that learning and inference are a little bit decoupled. So you train the model, and then at inference time, you can trade off compute for quality. You can use different kinds of ODE, STE solvers to trade off the kind of compute resources you have access to and the quality of the samples that you want. I think this is exciting because there's a lot of opportunities for improving the inference stage, taking ideas from statistics, from numerical methods, applied math, to figure out better ways to generate samples once you've trained them on. And kind of like the flip side of this is that it's pretty easy to steer the generative process in different ways. So if you have a pre-trained model, it's relatively easy to add conditioning signals or extra context that you can use to enable conditional generation, condition on images, condition on MRI scans, or condition on sketches. Everything falls out pretty nicely because learning and inference are decoupled. So it's actually possible to change the generative process in a principled way without having to retrain a model every time, just through rules of statistics and calculus. And there's been a lot of success in inverse problem solving, including from our group and other. Other recent advances, that I'm excited about, include incorporating preferences. So if you have user data in the form of preferences, like they would tell you, I prefer for this prompt, I prefer this image over that image, which is shown to be very important for training large language models. RLHF, reinforcement learning from human feedback, is very important in the context of large language models. We've recently kind of extended those ideas to diffusion models, a model called diffusion DPO, which is very exciting. And the images I was showing in this talk are actually based on that model. Also pretty excited about incorporating geometry and constraints, especially when we're thinking about scientific data. There are often natural constraints that we want our samples to satisfy, and incorporating them into the diffusion process can improve the quality of the samples and make sampling faster. So there's a lot of interesting research to be done in that space. And finally, I'll mention discrete data. So far, diffusion models have not been very successful on discrete data, for example, language. And the reason is that if you think about discrete space, there's no notion of gradient. So there is no notion of score. So there is no natural way of applying diffusion models to something like language. But we've made some progress in that space, and I'm pretty excited about hopefully being able to close the gap with autoregressive models and the GPTs, and be able to generate natural language or code or molecules using these kind of discrete diffusions, where we once again kind of generate data by turning noise into samples in a coarse-to-fine way, as opposed to left to right, token by token. We want to generate more, with this kind of a coarse-to-fine sort of approach that has shown to be so successful in images, but also video, audio, speech, a lot of continuous kind of modalities where these diffusion models have been really, really successful. And I think that's all I have. So thank you for your attention.
Thank you so much, Professor Herman. It was really, really interesting. So is there some question from the audience, please? There is some question. I have one question, Professor Herman, about your presentation. So at the beginning of your presentation, you show us very nice pictures. And from your experience, what is the most difficult picture or representation to generate with AI, artificial intelligence?
Yeah, it's a good question. I think the existing models, they have a lot of trouble generating hands for whatever reason. Probably because maybe they haven't seen enough in the training data, or hands are pretty complicated, but a lot of models struggle with generating hands. They also struggle generating text. So like if you wanted to generate a sign, a street sign or something, and you want to render text in an image, that's also challenging. And generally, they have trouble understanding relationships, spatial relationships between objects. So if in your caption you start saying, I want a table and I want an apple on the table, like you start making complicated kind of like spatial relationships between objects, they also struggle quite a bit in that.
Okay, thank you so much. There is another question, maybe, please? If no question, I have one question more, Professor Herman. In the approach that you use, the parallel computation, in which you show the both image and the video, is there some special measure to compare the both image, the image you generated and the image that the other algorithm generated, like dice measure, something like that?
Yeah, so in this case, basically, we can actually prove that they are indistinguishable. So, and you can use, L2 distance, or you can use LPIPs, you can use the usual SSM, usual kind of like image quality metrics to compare. But in this case, the difference is, there's no difference essentially, it's imperceptible. For the 3D, there is more difference. And that's because we're not actually trying to replicate exactly the sampling procedure. Right? It's a little bit subtle why, but that has to do with the kind of the way moment updates are performed in Adam. But in this case, there is more difference. We have not been able to quantify it well, because I don't think we have good automatic metrics. But yeah, that's something we should look more carefully.
Okay, I see. Okay. There is another question, please, maybe from the audience. Okay, so I have one more question, Professor Arnold. When these techniques are really powerful. I can see that they are really powerful. Just regarding the application, it is possible to use it for your experience again. Is it possible to use this kind of techniques to simulate a game which change very quickly? For instance, the ping pong. You can, for instance, create a game, but dynamically. It means put the ball at this part of the table, and you put the ball and the other, very fast. Is it possible to do that?
So right now, not like, I mean, it's possible to generate video, but it's it's very slow. So real time, it's images are starting to be something you can generate in real time. And so we're starting to see kind of like potential application to gaming or VR, AR, where people are starting to look into, like customizing worlds and game environments for users, maybe tailoring them to their experiences, to their preferences. So that's why people are so excited about even generating assets like this, where you generate a sword in as a 3D object from an image. This asset could be deployed in a game, right? So that's very exciting. But right now, it takes an hour to generate one of these things, right? So it's too slow.
Maybe it's possible, for instance, if we design the table of the ping pong and just give some orders to the ball that to move the ball, for instance. Is it possible to do that?
Yeah, so it might be possible to like use game engines and maybe not generate everything this way, but sort of like use kind of like a blend of generative AI and usual graphics and existing techniques. I think that's probably where the future is going to go.
Okay. So there is another question, maybe, please, for Dr. Erno. If not, I have the last question, Professor Erno. Sorry. In your presentation, when you present this core model, the core model is represented by SO, I guess, and that is a function from ear dimension to R dimension, right? The number of dimensions is impact in the model. More dimension is better, less dimension is better.
Oh yeah, so less dimension is better. Like high dimensional data is always hard, and that's actually why video, for example, is so hard, because like images, okay, it's doable. Even high resolution images, like if you have 1024 by 1024 pixels, it starts to become very big, which are like a million inputs, a million outputs. It's a lot of RAM that you need to train these models. But video is particularly hard because you would need, like if you have a lot of frames and each frame is an image, you quickly basically run out of memory. And that's why people right now, they cannot generate long videos with these kind of systems, because basically exactly what you said, the sort of, there is just too many inputs, too many outputs, and we cannot fit into even, with the latest GPUs, we can fit only so many frames, basically.
Okay, the dimension are the characteristics, right? The features.
Yeah.
Okay, and I guess it's the time computation is also height. More dimension. Okay.
Yeah.
Okay, I see. Okay, thank you so much. The last question maybe from the audience. No, it's okay. So, Professor Arnon, really thank you so much for your presentation. It is very interesting. I guess we meet in person in the next edition of SIMBig, maybe Peru and
hopefully
other
next
country.
time.
Yeah, I'm really appreciated your presentation, your time, your help for this conference. So thank you so much, Professor Arnon.
Thank you for having me.
Thank you so much.
Bye-bye.
Bye, Professor Arnon. Bye-bye. Okay, let's move on to the next presentation. Diego Johnson, Brian Mamani, Cesar Salas, please. You are here. Diego?
Hello.
Oh, hello, Diego. Please, can you
Good
share
evening.
your slides, please?
Yes, one second, please.
Thank you so much. So Diego will present the
connection
paper entitled Collaborative VR a social VR architecture for social interaction between college students.
Yep. Okay, can you see me?
Not too
Okay,
slides,
nice.
but I see you, but not too
Yeah,
slides.
perfect.
Not
Yes,
yet.
1 second.
Okay.
It's this.
Exactly.
How about now?
Okay.
Good.
You can start, please.
Well, good afternoon to everyone here. Today we're bringing you Collab VR. This paper explores the decline of social interaction in the university environment due to the adoption of online classes. Our proposal frames the use of VR, the creation of Collab VR, a social interaction platform. As the problem, the problem is that as a result, implementation and adoption of asynchronous or remote learning have been promoted. Although technologies such as learning management systems have provided the possibility to continue with online education, their use has generated challenges related to the decline of social interaction between the students. This decline is an issue that affects the quality of learning students' performance. According to a study, 71% of students experience negative effects on their learning due to the lack of interaction between the teacher and peers. Likewise, as indicated, it results in a sense of isolation and lack of motivations in the students, which negatively affects their commitment to the educational process. Some background for this problem. We firstly found that about 40% of young people aged between 18 to 29 years old have had a hard time with social anxiety. This makes it tough for them to socialize and therefore gain the skill they need to grow as a student and human. This issue intensifies because of the pandemic, which started the shift into a remote education and self-isolation. Next, we have to talk about the tools we use for learning online. These tools are great for helping us meet and talk to new people. Studies have shown that most of the students and teachers indicate there's a lack of interaction in these online classrooms that we participate on now. Lastly, let's not forget how fast online learning is growing. By 2025, it might be worth over $33 billion. This tells us that more schools or higher education institutes might start teaching online or mixing online with regular classes. While this could make it hard for students to connect with each other, it also gives us the chance to come up with new ways to help these students interact and socialize in a better, more connected future. Why is our study important? We examined two essential elements. First, we understand that talking, working, and connecting with others are not just a part of learning, but they are their heart. These interactions are key for students to develop fully, not just academically, but as people. On the other side, we are seeing a growing interest in extracurricular activities in higher education, particularly in developing countries. These are proving to be a powerful tool for students to grow their skills, to feel better about themselves, and to get ready for the real world. What's more, studies have shown that these activities can instill in students a strong sense of social responsibility, this way contributing to the development of a more sustainable society in their developing countries. So before delving into the architecture, which is our proposal, we first review a few concepts. What's virtual reality? Virtual reality is an artificial experience that immerses the user in a 3D space visually insulated from the physical world that can enhance communication among geographically dispersed group, like, for example, remote students. ADD, which is attribute-driven design, is a methodology that uses quality attributes as a basis to guide the architecture design process of a system. Lastly, domain-driven design. It's a software design approach focused on understanding the business side and the business domain and aims to reflect this structure into an application. Building an enterprise-ready architecture is important for us because we aim to give a service to universities which are enterprise-sized businesses. In our related work sections, we explored several key studies that can be grouped in the following categories. VR for educational events or educational activities. Studies shown that VR's unique ability to simulate real-world events, like a graduation ceremony, which can lead to improved social engagement and participant satisfactions in virtual settings. Psychological benefits of VR. Works on this field suggest that VR's immersive experience can significantly enhance psychological well-being, with a strong sense of virtual presence aiding in socialization and reducing the feeling of isolation. Third, we have communication and interpersonal skills through VR. Here, researchers indicate that VR can support communication as effectively as in-person interactions, fostering deeper personal connections and self-expression. Lastly, social VR for virtual learning. Social virtual reality's potential is incredible. They can enhance virtual learning platforms in a really incredible way. So we come to our contribution. In this paper, we proposed an architecture for CollabVR, a social platform in virtual reality aimed at promoting socialization among students. CollabVR stands out by enabling universities to create VR spaces that encourage interactions through extracurricular activities like clubs, cultural events, workshops, which aim to counteract the reduced social contact that students have during their online classes. Here we can see the main features of our proposal. In the first column, we can see the users we have identified, which are the students and moderators of different activities, and the administrators, which are the staff from the university that create these activities or design these activities. In the next column, we have the devices with which to access CollabVR. It can be through a desktop, like a computer or a laptop. It can be through your VR headset or through a phone. In the third column, we show the platform features, including social activities, user role management, VR activity data collection, session moderation, avatar management, registration and authentication, the visualization of VR activities, and also, of course, multiple users in a single session. With these functionalities in mind, we designed CollabVR architecture, following DDD domain-driven design principles and employing a microservice approach to enhance the modularity and scalability of our system. In this diagram, we can see the general workflow of CollabVR, identifying how the components interact with each other. We also see the key technologies powering the web app and VR applications, as well as the server infrastructure, which feature Unity. We use Unity for the creation of the VR platform, as we can see here, which communicates, We use Unity to create the VR platform, which communicates with Photon server to enable real-time communication between virtual reality environments. Angular for the client application, which allows the administrators to manage virtual reality environments. Both applications will communicate through an API gateway that will be in charge of directing the incoming requests to the corresponding microservices. Likewise, the communication between microservices is orchestrated through an event bus. Each service is insulated in a Docker instance, which modularizes our microservices, allowing greater independency and providing the possibility of an scalable system, and also ensures the availability of our systems at all times. For experiment, we defined the hypothesis that the Collab VR platform, based on the proposed VR architecture, has the potential to offer easy management, scalability, and effective performance for social interaction among university students. Our experimental protocol consisted in a virtual focus group of software architecture experts who evaluated the usefulness of our architecture and their functionalities. They were given 4 open questions with a linker scale response on the degree to which the proposed architectures contribute to social interaction, and to ask for suggestions for possible improvements. Our participants were 2 computer engineers working as software architects at companies like MTC and Seguros Remec, a Peruvian company, and 1 software engineer who works as a quality engineer at Snapchat and currently works at Blizzard. Our results are that all experts believe the proposed collab architecture have the potential or will enhance student social interactions. Our experts also sorry, this word is hard for me. Unanimously view the proposed VR solution as viable, especially as necessary technologies become more accessible, like VR headsets, increasing the chance of success of our platform. And also, they highlighted security as critical, with a strong authentication needed to protect the data and the user's privacy. Usability was identified as the most important quality feature because it's the experience that users will have inside Collab VR what will determine their experience and how they will interact or socialize. For management of virtual reality environments for extracurricular activities in universities can contribute favorably to the social interaction between university students, and that consequently the diminution of social interactions would be enhanced by the implementation of Collab VR. Well, we can see that we have carried out a bibliographic analysis from which we propose the architecture of design of Collab VR. We also saw the validation of our the experts that has been generally positive, highlighting the clarity and completeness of the architectural diagrams. And lastly, that Collab architecture has a significant technical potential to enhance social interactions among students in remote educational contexts. As future work, we can see the development of a virtual reality application following the proposed architecture. We can also see how we can evaluate the impact of Collab VR on social interactions, which would help to optimize our design and the functionality of Collab in the future versions, like increase better the usability based on users' feedback. And we can also explore the use of AI in Collab VR to identify, for example, students' feelings to promote certain extracurricular activities. That would be all. Thank you for your attention.
Thank you so much, Diego, for your presentations. It's very, very nice. So is there some question from the audience, please? Somebody have
Hello, thanks a lot. It is very interesting presentation. So I have one short question, like, do you measure like a spatial aspect in that case? Like, what is the influence on rural areas and in the large cities?
So could you repeat the question, please? The first part.
Yeah, so I'm saying like, do you have any mechanism that could measure like how what is the spatial features of a user, like where it belongs to, either it belongs to a rural areas like in a village or some remote areas, so like this.
Oh, like how we will see where users are from.
Yes, exactly.
Well, this collab, it's like a SaaS platform which it's only used for each university's students. So have the information for each student and they can like they can identify who is in which activity, right? So they will know where are they from. But we could also have a mechanism to identify where they are being connected from and maybe, I don't know, give them different features based on that.
Yeah, thanks.
Thank you.
Thank you so much, Asif. There is another question, please. I have one question, Diego. You use the virtual reality, sorry, but why not the mixed reality? In some cases, the virtual reality, the devices of the virtual reality are very invasive, but the other one, on the other side, the mixed realities are very, very, you're not really a big device, but it's small and very easy to use, etc. So did you think about that?
Yes, we've explored the use of, there's some software systems that help you, for example, simulate the use of a headset or a VR headset. And instead just use your camera to detect like, and based on that, to display your avatar in the virtual environment. That way you can be without the headset, without that invasive soft hardware, but also be present in the environment. Mixed reality, we did, what's the word? Sorry. Contemplated the option to integrate this, but would draw a line to the extent that we were going to explore on our study.
Okay, thank you, Diego. It's a very interesting project. So thank you so much, Diego.
Thank you.
It's yeah, and let's move on to the last presentation for today. So we invite Diego Sanchez, John Silva, and Cesar Salas to present the paper entitled CLP Safe Mobile Application for Avoid Cloned of License Plates Using Deep Learning. So, you know, is the idea.
No.
No.
Hi.
Yeah.
Yeah, John.
Please, can you share your slide, please?
Okay. I'm
It's okay.
representing.
Yeah. It's okay.
Yes.
Yeah.
I'll turn on my camera.
Okay.
Okay. Hi. Well. Hello everyone. Today I come to present our research. I'm John Silva Charmer, and my partner, it's not here, but is Leo Sanchez. We are students at the Berlin University of Applied Science. Let's start with the title: mobile application that allows detecting identity theft or of virtual license plates in metropolitan Lima using deep learning. We've carried out this research. First, we have the material methods, the index, where we define bullets or points we are going to discuss today. We have the material methods, starting with vehicle identity theft, that is a crime that involves the legal use of a vehicle's identity by another person. Vehicle license plate detector is a license plate detection technology, is a computerized application to recognize license plate images captured through images and videos. Also, the main method used here is deep learning, which is a branch of machine learning that trains computers to perform human-like tasks. Continue with the main problem. We have here is low efficiency on the part of the PNP, the National Police of Peru, in the detection and reporting of spoof virtual license plates, and some of the causes are, well, first, we have the absence of portable and light tools that allow speeding up the consultation process and report issues. Also, we have the ineffectiveness in usability and consultation on government platforms. Another cause is the slow communication channel with consultation service operators. This happens with when the police officers tries to communicate with an operator using the number of license plates to get the information of the license plate. And the last cause is difficulty in recognizing vehicle license plates in different scenarios. With these terms already defined, our main objective, or general objective, is to implement a mobile application to detect vehicle license plates that are under suspicion of vehicle identity theft in metropolitan Lima using deep learning. To begin with the analysis of a proposal, we carry out two main benchmarks, to analyze and determine the best tools for the development of application. We first define the characteristics to compare, such as the characteristics to compare these technologies. In the first benchmark, we did compare technologies such as TensorFlow, YOLO5, Fast RCNN, Detectron2, and we are going to use for the application development TensorFlow. Also, in the second benchmark, that was for the technologies of optical character recognition. Sorry. We compare different technologies such as ECOCR, AVI Finer Reader, Tesseract also, and the winner was ECOCR, that is more light with our project, with our research. Also for the backend of the application, we are using Python with Django, just to send the photos and the photo to our algorithm. For our mobile application, we're using Flutter with Dart. Here we have, with the design of the application, we have a solution architecture where we have our two main principal users, that are the police officer and the citizen. These users use their Android phone to take a photo, and this photo will be sent to our algorithm, and we'll make the query in the Suzerain platform to retrieve the information of the license plate to the police officer or to a citizen. In the case of a police officer, it will also have the possibility to file a report if they find something unusual in information of the license plate. And and this will be reported to the corresponding authorities. For the development of the application, just to explain a little bit, is we sent a photo to our algorithm, and this photo is loaded where the vehicle license plate can be seen, and a filter is applied to mark the edges, and with the edges already marked, the vehicle license plate is detected, which is where the largest number of edges are found, and then we focus only on the plate, and a cut is made on the image according to the coordinates of the edges. And using this easy OCR, we read the text of the images and thus return the characters of the vehicle plate. I have a video here to explain better. We'll see in the later. But to continue with the validation of our application, we had our main users, the police officers and citizens. We did a questionnaire for them in which they can make use of the application's functionalities and evaluate them. For this, we mainly find 3 scenarios that are defined as follows. The capture anchors are maintained in the 3 scenarios and the operating system, which is Android. The only variables or variations per scenario are mainly the distance in the photos of the vehicle license plates and the visibility of the vehicle license. Also in the scenario 3, another variable is the nighttime. We ask the follow question for a questionnaire that are mainly focused on the functionality of the application. I'm going to say the main 3 that are how intuitive do you find a CLP safe interface for recording license plates of suspicious vehicles? How do you evaluate the application's processing speed when performing license plate searches instantly? And is the license plate recognition function effective even in low lighting or variable visibility conditions? For our results, here are the results of our questionnaire, where the majority of users, both citizens and police officers, agree that the functionalities of our application are very useful to the detection of license plate fraud, especially for the police officers that consider it will be very helpful for them just to get the information as soon as possible in the moment when they are conducting a scene. And this is a graphic where our results of each question are marked. Our final conclusions with this research and project with our mobile application is mainly the project proposes to provide the opportunity to streamline the process of consulting and reporting cases of vehicle identity theft through a vehicle license plate detection functionality that allows the registration and notification process to be carried out to a corresponding polygon entity. Another conclusion is that the project can serve as a basis for the creation of different applications that aim to prevent the increase in the number of detectors in a specific sector in the country by detecting registered vehicle license plates. This is the final slide, but I would like to present to you the demo of our application, our mobile application, which is here, just to share to you how it works. Here we have the mobile application where we are testing the functionality of a camera. First, we load a photo of a license plate. We touch the button of analyze. It takes some seconds and it gives you the information of the license plate that we are trying to get information. And well, that was all that I have with this research.
Thank you so much, John. It's a very interesting work. So maybe the audience has a question, please. I have a question, John. You performed a survey for capture the opinion of the users, but how about the prediction algorithm? What is the accuracy of the recognition algorithm? Did you calculate?
Yeah.
Maybe I missed this part.
Well, it's not shown here, but the accuracy of the algorithm was high compared to our related works. I don't remember the exact number, but it was more about 80%. Even here, I have it can be well, it's not shown here, but yeah,
97 maybe. But 97 is very high. Maybe there is an overfitting. Did you?
Well, it depends more of the scenarios. We discussed the accuracy in the nighttime. It's in the first scenario when it was nighttime.
Yeah,
the accuracy was lower than the first and second.
Of course, yeah. Okay. Last question for me. You know, Peru, there is a lot of cloned plagues. You know, did you test to the cloned plagues with data from cloned plagues?
Did we test cloned plagues?
Cloned plagues, placas clonadas.
Sí, claro.
Yeah. Did you test that? Is the same results? You found the same results? Maybe? No, I don't know.
Well, the clone plates we didn't test like that because we had a restriction with the database of the government or police or system police. But we test with almost 30, 40 that's what I like. 40 plates with the Sutran query system where we can get the information of a vehicle.
Yeah.
And it was more like the same of the application we developed.
Okay. Okay. Okay, so thank you so much. It's all for me. Now, there is another question maybe from the audience? If no, okay, thank you so much, John. Thank you so much for your presentation. And thank you so much for your interest in SIMBig. So, Hiram, okay, maybe I can share my slides. Yeah, so maybe just for close the conference.
Of course.
Tick, tick. Voila. Tac. Okay. So here maybe you can start, maybe. Or no, maybe me.
I'm really fine. Just leave me. Yes.
Okay.
so that your slides, while your slides open, well, I want to thank you very much to you, Hugo Alatrista and Antonio Locio, for organizing this superb SIMBig 2023. And as we said yesterday during the dinner, I think it's a very notable fact that this is the 10th edition of SIMBig, and that we are very honored to have it hosted here at the Center for Computing Research, Centro de Investigación en Computación del Instituto Politécnico Nacional. And we are very happy to have all of you here in presential form as well as virtual form. And I have been here listening some of the presentations, and I think that the quality of this conference has been very good. And also yesterday I heard something similar from the keynote speakers. So, well, I think I just want to say thank you. I know it's lots of work preparing this, doing the program committee, and well, lots of things. So thank you, and this is a deep thank you for all of you.
Thank you so much, Hiram. And for us, we are very honored to organize SIMBig in your institution. I guess this is the first time that we moved the conference to another country, and it was really amazing. And I'm not there over there, but because I am actually in France, and it was difficult to me to move to Mexico. But I see that it was a very nice experience for all people that come to Mexico to attend the conference and to visit this beautiful country. Thank you so much, Hiram, for your help, for your organization, and we hope that maybe next editions will count on you again. So thank you so much. Thank you so much for all the people that see us. See us in YouTube, I guess.
Yes, we are transmitting on YouTube. So also thank you for all people watching us there.
Okay, thank you so much. So we close the conference.
Yeah, just I'm afraid your presentation, we are just looking the docs.google.com window. So I don't know if you are projecting some slides.
Sorry, no.
We see only the click to exit full screen.
Okay, sorry. Yeah, I will again to share my screen. Sorry, this is not.
Yeah, good. Now we can see it. Very good.
Yeah. So thank you so much for your interest in SIMBig, and see you next year.
I hope so. Everyone is here as well. Please submit to SIMBig 2024. That might be in Peru or Brazil. We are not sure yet, but I hope we can meet again wherever it's taking place. And thank you also to all our speakers, the ones that are here present. Thank you for your messages in the chat. So same from us. Thank you very much.
Thank you so much. So thank you, Hiram. Bye-bye.
You're welcome. See you again.
See you.
Goodbye.
Good night. Good afternoon for you.
Yeah. Thank you.
Bye-bye.